Okay, fine. Am I audible?
Yes,
Yes, sir.
yes.
Okay, fine. So sorry for the delay. There was some issues. Fine. So let's start the first revision session. So before starting the session, let me ask all of you that in week, so this would be a revision session for week 5 and 6, and the greedy algorithm week 7 and 8 would be taken by Atul sir tomorrow. Not tomorrow, I mean on Friday. So which topics of week 5 and 6 do you guys feel more difficulty in? I would be discussing some problems from the mock exam that has been released, and in general also problems I would discuss. But before that, which topics do you feel you are facing problems? And
Algorithms.
Sir, Floyd-Warshall algorithm.
Yeah, same here. Floyd
Yeah.
Warshall algorithm.
what Warshall
Graph.
algorithm? Okay.
Prince and
Alpha-Kruskal algorithm.
Prince Kuskal and Floyd Warshall.
Since this would be the revision session for your quiz exam, so my focus primarily would be on maybe, I mean, I would discuss if you have doubt, that is fine, but I would focus more on the problem solving part of it. So let's say, do you understand when you say you have doubt in Kruskal's algorithm? So what I mean is you should be aware of that basic theory of Kruskal's algorithm properly, and you should be able to solve problem using Kruskal's algorithm. So is that part okay, or is there doubt in that, or is the theory part fine, but you have doubt in the code? So yeah, I would prefer more doubt, at
A
least in
doubt in
the
the code.
doubt in the code. Okay, so
If you can explain theory also, it will be fine because to get back to the code. I mean,
okay,
if you have revised
okay.
the theory.
Manan, can you
Yeah.
please readjust your mic? I think it's
Hello.
yeah, you're audible, but noise is coming. Like it's like the mic.
Yeah. Hello. Hello.
Yeah, you are audible, Manan, but the problem
Yes.
is your mic is getting a little bit noisy. It's fine. It's
Okay.
okay. Okay, so Floyd-Warshall algorithm. So before going to Floyd-Warshall algorithm, so let us do the normal part. Let me ask this question. So given a graph, okay, given a graph which has negative edges, so is it always the case that Dijkstra algorithm wouldn't work? Negative edge.
No, sir, it could work,
No.
but
And if the same graph, that means which has negative edge but not negative cycle, I mean, so when we say Dijkstra algorithm can work, I mean, so let me frame it in this way, that if a graph has negative edge but not negative weighted cycle, can I always say Dijkstra algorithm will work, or can I always say Dijkstra algorithm will never work? So
it would be may or may not.
correct,
Yeah,
correct.
depending on the
Yeah,
depending on the product.
yeah, so that's very important. Keep that thing in mind. So let's say if a graph has been given to you in a question, and it might have some negative edges in that, might not have a negative weight cycle. If it has a negative weighted cycle, then you can always say that Dijkstra would never work. Not only Dijkstra, if a graph has negative weighted cycle, that means the notion of shortest path is undefined on that graph, right? Because if it has a negative weight cycle, you can just go around that cycle infinitely many times, and thereby reducing your path length every time by some constant factor, and you can go up to minus infinity. So the notion of shortest path does not exist if a graph has negative weight cycle. But if it has some negative weighted edge, then the shortest path might, then Dijkstra might or might not be able to calculate the shortest path properly. Okay, so just by seeing a graph, in fact, this kind of question might come, and I think in mock one question is there that a graph is given, some negative edges are there, it might or might not have negative cycle. You have to tell whether Dijkstra would work or not. The only way to confirm that is you have to run the algorithm and check whether it's working. Fine. So maybe in the mock a little bit more involved example is given. In the exam, so much time taking example might not come, but conceptual questions on these topics might come. Okay. So see a negative weighted edge in a graph, we don't take risk. I mean, in reality, I'm talking. We don't take risk by in order to check whether Dijkstra would work or not. Rather, we simply apply Bellman-Ford. Now, Bellman-Ford algorithm, the benefit of Bellman-Ford algorithm is it can detect negative weighted cycle. So how will it detect negative weighted cycle? So let's say what does the ith iteration of Bellman-Ford algorithm says? So when I am, let's say I have 3 for loops. The first for loop, outer for loop would run, let's say n times, right? N times it would run. Actually, I prefer to write it as like this. First n minus 1 times it would run. And next what happens is I would for all edges, right? Let's say for all edges, u comma v, I would relax, right? What is relax u comma v? So by the way, what is the relax operation? Relax operation is nothing. If your distance of v is lesser than, greater than distance of u plus, let's say your a list or a matrix, right? Adjacency matrix of u comma v value. If it is so, then you simply assign distance of v as this thing, right? So this is basically your relax operation. So in Bellman-Ford algorithm, what do we generally do? The gist is you run a loop for n minus 1 times, and what do you do is then you have for all the edges you relax the edges, and after that, what does this mean? So when I'm running the loop at ith iteration, what does that tell me in Bellman-Ford?
Once again, sir.
So when Bellman-Ford algorithms, this outer loop is running, let's say it runs for n times only, fine, no issues.
Okay.
So if I run the Bellman-Ford algorithm outer loop n times, right? So at the ith iteration, when some, at the ith iteration, what does that ith iteration mean? So when my Bellman-Ford algorithm has the iteration, ith iteration is completed. So what can I tell about the state of this distance dictionary at that point? What does it mean? What are the value inside the distance dictionary at that point mean?
All distance from the source path is shortest. If
At
there are, if there are no negative cycles, and if it after nth time also it changes for the next iteration, then there will be a negative cycle. But if it is for n minus 1 times, if it runs, then all the shortest part would be there.
I was asking a little bit the internal part. So what I mean is, so let's say when this for loop, when it is at its ith iteration, right? Some ith iteration,
Okay.
ith iteration.
Okay.
So that means what? Ith iteration means what? When I have completed the ith iteration, not at. Let's say when I have completed ith iteration of the for loop. So what happens actually is the distance matrices, the distance dictionary, sorry, not distance matrix, the distance dictionary for all the vertices, whatever value it will have, right? What does that value indicate? That was my question. In between the iteration, not at the end of the iteration.
Sir, it will give the minimum distance using I number of edges.
Correct. That's the main thing. So When your I iterations are done on Bellman-Ford algorithm, I mean this code, if you see, when the ith iteration has completed, right, at that point, whatever value is there corresponding to each vertex inside the distance dictionary, that gives you the minimum distance from whatever source vertex you are working on, from there to that particular vertex by only using I edges. Okay, so let's say a graph is something like this. I have, right, some graph like this. Now you can see in this graph, there is no direct edge between D and B. Okay, so right, there is no direct edge between D and B. So the adjacency matrix of this graph would have a 0 corresponding to the D and B index position, right? But when I run, but if you see that when if I try to make a path from D and B, then I would get, can I have a one length path? It's not possible because there is no direct edge. Can I have a two length path?
Yes.
Where? From D to B.
B to C, then C to D.
D to C, C to B, how can I go there?
Three length
C to
paths.
C.
Three length path is there, two length path is not there in this graph. So if I want to go from D to B, then two length path and one length path, both of them are not there. So only option is three length path, which is D to C, then C to A, and then A to B, right? So three length path. So the thing is, so when I run the Bellman-Ford algorithm, initially the distance, this distance dictionary for each vertex would be initialized to a maximum value, right? Some more value. Now let's say some positive infinity, so you can use float inf in Python to do that. Now every iteration, when I in the first iteration of the outer for loop, not every, in the first iteration of the outer for loop, the value between this D and B in the distance, I mean your distance dictionary starting from D, let's say I start the Bellman-Ford from D and I have to find the distance till B, so the value of B would still be infinity because I don't have a direct connection. When the outer for loop iterates through the second iteration, then also I would not get my, and I mean the value at B would still remain infinity because I do not have a path of two length also. But when the outer loop goes through its third iteration, then I would get a positive, then I would get a path length, right, corresponding to whatever this length is, this length, that would be, that I would be getting in the distance of B. Fine. So why? Because so what does that mean? So that means I have a path from D to B, which is of length 3, and that's why in the third iteration of my outer for loop, I got the a finite amount of path length. Until and unless I get to that point, I had infinity in B, right? So Bellman-Ford's ith iteration tells you minimum path length between the vertices, right? Between pairs of vertices, considering path of length and I mean I. At the ith iteration, after the ith iteration is done, it means I. So what is the meaning of path of length I? A path consisting of I edges. So if that is the case, what I would rather do is, if I take any graph, right? What is the meaning of a path? Any path means it is a tree, right? All these things I have discussed in the main session, I mean the open session as well. If you have doubt, you can visit there. So any path in a graph between any two nodes is basically a tree, correct? Now a tree would have always how many edges? If n vertices are there in a tree, it would have n minus 1 edges. Now if a graph has n vertices, so the path would be, what is the path connecting all these vertices? It would have maximum n minus 1 edges, right? Such a path. So therefore, I can always guarantee that whatever pair of vertices you consider within the graph, I can always guarantee that the path from any two random pair of the path between any two random pair of vertices would always have at most n minus 1 edges, because the tree, the graph itself has n edges, right? So if the path length is n minus 1 maximum, it can be maximum n minus 1, right? And I just told that Bellman-Ford's ith iteration of the for loop gives you the path, the shortest path of I length. And I just now realized that my any path would have at most n minus 1 edges. So what does that mean? If I run my Bellman-Ford this outer loop for n minus 1 times, right? So I would actually get the shortest path between every pair of vertices, considering all the edges, because at most I can have n minus 1 edges in a path. So now at this point, whatever may be the value of, after this code is completed, at this point, whatever may be the value of your distance dictionary, right? Distance dictionary for all the vertices, right? For all the vertices. So these are just pseudocode. Don't take it seriously. I'm just trying to, I'm meaning to say that all the vertices value of the distance dictionary would converge to the shortest path. Fine. Shortest path length, I mean. Now, in one case, it would not be so, in which where we would have a negative weighted cycle. Now, why is it so? Because if I have a negative weighted cycle, then what happens is, so at first, let's say that if we did not have a negative weighted cycle. So if we did not have a negative weighted cycle, so even if I would have run this loop one more time, nth time, right? Let's say this n minus 1, I change it to n. So even if I run this loop at the nth iteration, then also there would be no change in the distance dictionary. Why? Because I told that anyway, any path length would have n minus 1 edges. Any path, not path length, any path would have at most n minus 1 edges. So once I do it for n minus 1 time, that's it. After that, if I do it for 100 more times, that doesn't matter. There would be no change in the distance dictionary, because you have considered the whole path, considering all the edges, right? So basically what will happen after that is, if there is no negative weighted cycle, this relaxation operation would not happen. So basically every time your distance v, this condition would fail, right? So that is how it would work. But if I have a negative weighted cycle, then what happens is, so even after considering n minus 1 edges, there can be a situation where, let's say I have a cycle like this. Let's say, is this a cycle? Yeah, this is a cycle. So let's say 2, 4, and minus 8. Right. So if you see that this is a negative weighted cycle that I have over here. Right. So what is the value? The negative net value? Net value is minus 2 of this negative weighted cycle. Now the thing is, in this scenario, if I run the iteration one more time, the nth time, then also the distance vector would reduce. Why it would reduce? Because considering any n number of node can be connected by n minus 1 edges. That is fine. And if I try to connect it with, if I try to add one more edge inside it, even though it is connected, but let's say I want to add another edge inside it. Obviously that edge, if it is positive edge, it would add some amount to the path length, obviously, because it's a positive value. But if I try to add an edge which has a negative total value, such that it is so much negative, it is also reducing this, it is more negative than the summation of these two path length, these two edge length. In that case, by adding an edge, by creating a cycle, actually I am able to reduce the overall path length, right? So that's why the nth iteration of Bellman-Ford, if that iteration changes the value of your distance dictionary in any of the node, if the nth iteration of Bellman-Ford algorithm changes the value of your distance dictionary in any of the node, even if it changes in at least one node, right? Then you can tell that the graph has a negative weighted cycle. So at this point, after this loop is over, right? After this for loop is over, let's say it is over at this point, suppose, right? Outside the for loop, you can just copy your distance dictionary into some distance 2 dictionary, right? And then for one time, just once, what you can do is, for all edges, u comma v, relax, u comma v. Just do the nth iteration outside this for loop. Now, if this iteration changes your distance dictionary, so now here you can check if your distance to dictionary is not equal to distance dictionary, right? In this situation, you can say that print there is a cycle. So that's how Bell-Manford algorithm helps us. And if there is no negative weight cycle, right? If it is not the case else, then you can print the distance dictionary. I mean, right? Because that's correct. So cycle is not there, negative cycle is not there, it's fine. So this is how Bell-Manford algorithm works. Obviously, you see that this I have written all edges like that, but if you have to execute it in a matrix, it would be a two loops, right? Because you are traveling through a matrix, so 2D matrix of adjacency matrix, so that would be a n squared time. So this actually boiled down to n squared time, and this tells you order n time, right? So n minus 1 or n whatever. So basically this Bell-Manford algorithm is n cube time. Even if you consider it in terms of edges, so since I'm doing it for all the edges, so how many edges? Let's say m is the number of edges and outside loop is running n times. So n into m is basically your time complexity. Now n cube and n into m are basically the same thing. Why? Because the number of edges would be in terms of order of n square in case of a complete graph. I mean, or let's say the graph is nearly complete, right? So basically it would be anyway n cube. So this was Bell-Manford. Dijkstra we discussed. And after this, now I would go to the Floyd-Warshall part. So benefit of Floyd-Warshall is it's a kind of a dynamic programming approach. So anyway, it helps because it has overlaps, and that's why if you use it in a dynamic programming manner, then it reduces the overall time. So what is the idea of Floyd-Warshall now? From problem solving perspective, I'm telling. Let's say take a graph, okay? After that, we would check the code, but before that, let's solve a problem. Mm. Fine. I'm taking undirected graph as of now, whatever. Just tell me some values. Negative values also is fine. Let's
2.
say 4, 2.
-6.
Uh,
5.
okay. Oh, yeah, fine. Okay. And let's say -2. Fine. So how to do the Floyd-Warshall questions? Fine. So what is Floyd-Warshall? Before going to Floyd-Warshall, can anyone tell me what is a transitive closure of a graph or of a matrix in whichever manner you want to say? So let me ask in this manner. If I have an adjacency matrix of a graph, right, like something like this. Suppose this is an adjacency matrix of a random graph. Okay. So this is, let's say, A. If I write a to the power, let's say a square, right? If I multiply a with itself, so obviously these values would change. What I want to ask is what would those values indicate? Considering
If
this
the
is a graph.
path of length 2 from one point to another.
Exactly. So path of length 2 means 2 edges from one point to another. So likewise, if I say a to the power k, that means path considering of edge, I mean any path which has k edges between two nodes. So wherever I would get 1 in a to the power k, that would indicate that I would have a path of k length between those two vertices and the 1 at that position in the matrix would indicate that. Okay, so that's what transitive closure is. In Floyd-Warshall algorithm, what we do is, when I write a to the power k, so what is a? A is, let's say, adjacency matrix of our graph. And when we write a to the power k, what we mean is considering k minus 1 vertices, right? Considering k minus 1 vertices. So 0 to k minus 1 vertices. So by using 0 to k minus 1 vertices, what is the minimum path length between every pair of vertex? So if I draw it like this. So at this point I would write this is 0 0, so it is anyway 0. So let's say at this point, right, 0 1, 0 2. Let's say not. Let's take example of this value, which would be what, 0 1 2, and this would be 2 1, right? So what I mean is, from second vertex to the first vertex, what is the minimum path length by using 0 to k minus 1 vertices? By using 0 to k minus 1 vertices. So what do we mean by using? By using means, I can have any vertex from 0 to k minus 1, right, as my intermediate steps in reaching from 2 to 1. Right, I can go from 2 to some vertex less than 0 to k minus 1, and from there I can go to 1, right, any of the vertex. Now whatever is the minimum path length among all these possible paths, that I would put at this place. So this is the definition of Floyd-Warshall's, so this is the setup of Floyd-Warshall's algorithm. Now the thing is, as we told, that Floyd-Warshall is a dynamic programming algorithm. So how it works is, likewise we would have a recurrence relation. So how does the recurrence look? So A, let's say A is the matrix which stores the path length, right? A of, let's write it in this manner, that I have the path length in order to reach from AI to J using, okay, AI to J using, let's say, k vertices, right? Using k vertices is given by, now the thing is, when I'm writing aj to k, what does that mean? That I can use vertices from 0 to k minus 1. So ai j k is, I can go from ai to, let's say, a k minus 1, and obviously by using k minus 1 vertices, right, plus the distance of, now from k minus 1 I would go to j k minus 1. Okay, now the thing is, I can have many such k's. I can break it up into any place. So what I have to do is, I have to make, oh sorry, either this, right, or I do not go for k, the kth vertex at all, right? I don't want to go, and I can see that my direct distance is actually better, right? So that would be a of I to j k minus 1. So this is the direct distance without going for any intermediate halt. If that is better, then I would consider that only. And you have to minimize this thing, whichever is the minimum, over k. So minimize this over k. So this is the Floyd-Warshall's algorithm's basic concept. So now we would take this graph as example and run the algorithm. And then coding, all the coding doubts I would discuss at the end if we get time. Fine. So how to do it? Right? Okay, I think I drew a lot of vertices. Let's search 5, right? Anyway, it's fine. Or let's the sake of, let's take 4 vertices. It would be quicker. So 0 1 2 3. Okay, so 0 to 0, I mean not 0, right? A, B, C, D. Now, in our this recurrence relation, it's not A, B, C, D. We are using K. That means we have to 0, 1, 2, 3, 4. But anyways, you get the point. Just consider A is 0, B is 1, and likewise consider. Now, so when I would, so when I'm writing this Aij is basically the index position, and over here at the top, I would mention what is the K value, right? So at first A is 0. From 0, we would start. So what does this mean? This basically means that you are not using any other vertex. It's as good as the adjacency matrix directly. So adjacency matrix A to A, since we do not have self loop, so we would consider 0 anyways. So it's always 0. A to B, I have -2. A to C, I don't have any path, so it would be initialized to infinity. Not path, I don't have any direct edge, right? And A to D is 4. B to A is -2, 0. B to C is 3. B to D is 2. If I make some mistake, please point me out, okay? During, I mean, if I while writing, if I make some any error. So C to A is infinity. C to B is 3. C to C is 0. C to
So
Yeah.
shouldn't the graph be directed?
It doesn't matter, right? You can, I mean, when it's not directed, you can consider it as both ways,
No,
bidirected.
won't it be possible, like if we go from A to B, then it is -2, then again from B to A, again -2, so total is -4.
Sorry, I didn't get what?
Like if we, currently we have A to A 0, right?
Yeah.
But if we go from A to B and then B to A, then we will have -4.
Oh, no, no. What I mean, okay, that's fine. You can consider directed graph. Okay, let me give example with directed graph only. I will make it directed. But why I would go from A to B even if you do not consider directed graph? I can grow from A to B and B to A. Why I need to go? I mean, it would not happen like that because it's once visited. You have the visited condition, right, in the code.
So we are finding the minimum distance from one point to another, right?
Yeah.
So technically from A to A, the distance will be negative infinity because you can continuously go to B and come back to A.
Oh, so that's what I'm saying. Yeah. So if you use undirected graph in that respect, you have to make a little bit change in the code. You have to use the visited thing, and then you can figure it out. Okay. That, I mean, you can use undirected graph in Floyd Warshall also, just by making a little bit change.
Okay.
But okay, fine, no issues. If just for the sake of example only we are doing. So, anyways, let's take directed. But then I have to. Let's take a cycle. Let's make this cycle also. Fine. So now I have to change the matrix now. A to B is -2. That's fine. But A to C is okay. A to D. A to D is 0. I mean infinity. Sorry. B to A. C to D is infinity as well. And D to A is 4. D to B infinity. D to C is 5. D to D would be 0. Fine. So this is my adjacency matrix, and that we represent by A0. Then when it becomes A1, so what do we mean by A1? The idea is by using the first vertex, okay, or A, by let's say by using A as an intermediate step between every pair of vertices, what are the minimum distance that I can get? So how will we do that? So A to A would be, let's say I don't want to make any change with that. So what should I write in place of A to A? I mean, I by using A itself, I can reach A in what, how much amount of distance? Doesn't change, right? It becomes 0 only. I'm not making any change. Now by using A to B, by using A. So what does this mean? This means by using A, because using A as intermediate. Why? Actually, this arrow should go here. So because of this one. So by using the first vertex as an intermediate. Now, so therefore this line would anyway be same, right? Because here I'm going from A to any other node. So there is no question of using A itself as the intermediate because A is the source. So keep it as whatever it was. Now I would, from B to A, it again remains same. Doesn't make any difference because I'm going to A. Now B to B, if I go from B to A in this case, right? Can I go from B to A? So this is where you are telling that it would get minus infinity. I can go from B to A, then again come to B if it is bidirectional, and it would go on I mean, it would, I can reduce it to minus infinity. So for others, I'm telling. So at this point, if I want to fill up this position, right, B to B, if this is bidirectional, I mean, or undirected, what I mean is undirected. So what does that mean? I can go from B to A as the intermediate, because that's what I'm trying to do, using A as intermediate. So B to A and then coming back from A to B, right? So therefore A is an intermediate, although my source and destination is B only, but I'm using A as an intermediate. I'm traveling to A, then coming back from A to B. So therefore I would get this -2 if it is undirected. Undirected means I can go in both the ways, right? So then -2 would be -4. Or I can repeat that multiple times. So that way it would be a problem. But the thing is, you can take care of that by making a small change in the code. So Floyd-Warshall algorithm can work in undirected graph also. That's not a problem. But in our syllabus, I think we are only dealing with directed graph, so it's fine. So let's take this example. Now, since this is directed here, I cannot go from B to A, right? Because I can only come from A to B. So do I need to make any change here? No. So B to B is 0. Now B to C. Okay. So what does that mean? I would go from B to A, then come from A to C. B to C means that. Now, what is the distance for that? B to A, how much distance is it from B to A? Whenever you consider this, when you are filling up this matrix, right, you consider the distance from the previous one. Okay, because that's from that is the current state. So you consider B to A, what is the distance? I cannot go from B to A, right? It's infinity. So the B to A itself is infinity. So therefore, this would be, I mean, this would be what, I mean, now I can, if I take this path, it would take me infinite distance. But initially I had what? B to C was 3. So whichever is less. So infinity is less or 3 is less. Obviously 3 is less. So therefore I am this minimum is coming into action, and I would pick the minimum one, which is 3. Okay, then B to D. So take A as intermediate, B to A to D. Same thing, again it would be infinity, I cannot reach, therefore this remains as it is. Right? C to A. C to A, can I go from C to A by using A as an intermediate? No, as of now, no. So it would be anyway infinity, I cannot reach from C to A. C to B, as A as an intermediate, so C to A to B, not possible because I don't have any path from C to A. As of now. C to C, 0. C to D, again I cannot go to A, so it remains as it is, which was infinity. Now D to A, was 4, so A is itself 4. We will not make any change. D to A and A to B. That's for this position, right? D to A and A to B. So what is D to A? 4, right? And what is A to B? It is -2. So 4 plus -2 is positive 2. Correct? So D to B I can reach by using A as an intermediate node by using a 2-length path. Okay. And what was my initial distance between D and B? It is infinity. Right? So whichever is minimum, 2 minimum or infinity minimum, 2 is minimum. So put 2 over here. And that's it. Like this you would proceed. Now D to C by using A as an intermediate, same thing. D to A, A to C. D to A is how much? 4. A to C is how much? Infinity. I cannot reach. So basically this boils down to infinity, but initially I had what? 5. D to C was 5, right? Directly D to C was 5. So whichever is less, 5 is less, infinity is more. So take 5. D to D, let's say 0. So this thing, this matrix now indicates by using A as an intermediate vertex, that means since only A, the only one vertex is there as an intermediate vertex. So this means by using A as an intermediate vertex or by using a path of at most length 2. That means by using a path of at most 2 edges, what is the minimum distance between each pair of vertices? Fine. So that this matrix is representing. Likewise, one more iteration I would do, for example. Now this would happen for the next K value, which is 2. So A of 2. Okay. Now what does this 2 mean? By using, what should I write? By using?
B as intermediate.
That's the problem. By using either A or B as intermediate or both. So basically now you have options. Remember what did we tell? When I am writing K, that means I am allowed to use, that's why I asked this, allowed to use 0 to K minus 1 vertices. Right? So now this means by using 0 means here A and 1 means here B. So by using A and B as intermediate, not and. So what I mean to say is you can use whichever is best. You can use either A or B or both if you need. That means you have at your arsenal these 2 nodes in which you, which can act as intermediate vertices. Now, if you have a path which is going from, let's say, some C to D, using A as an intermediate, not in this graph, I'm just arbitrarily saying, let's say in a graph, there is a path from C to D using A as an intermediate, and another path, C to D, same, but using B as an intermediate. Now, you can compare between both of them, whichever is less, you can pick up. Or let's say there is such a path which is going from C to A to B, and then B to D. So you can do that also. Fine. So therefore keep this thing in mind. This does not mean that when I'm at K, it does not mean I can only use the K minus 1th vertex. It means I can use any vertex between 0 to K minus 1. Okay. So by using A, not and, I think I should write or. Yeah. Using A or B as intermediate vertices.
Sir, I have a doubt here.
Yeah.
So this will be taken care of by the previous matrix, right?
Exactly. This matrix.
Yeah. Okay.
That's the point. If you go for this matrix, then you have to consider for A and B both possibilities every term. Every time you calculate Aij over here, you have to consider both A and B, whichever intermediate is giving you better result. But instead of that, if I do it in this matrix has already done it using the A, right? So the best case possibilities for A has already been done in this matrix. So if I use this matrix and compare with only B possibility, I mean only by considering that B as an intermediate vertex, and compare and do the task over here, right? So that would always compare A implicitly. So I need not compare, since here I am writing A or B. So both options are there. Both I can use an intermediate, but I need not check both, because if I use it using this matrix, in this matrix the best cases for A has already been taken, because A was considered as the intermediate over here. So I would only consider B as an intermediate node on this matrix's value, and that would implicitly take care of both A and B cases, right? So that's the very important point. Thanks for raising that. We would every time you calculate A of K, you take the distance from A of K minus 1, right? Just the previous one. Like when I calculated this, we took the distance from this. When I'm calculating this matrix, take the distance from this one. Fine. You can also do it on this one, but then you have to calculate the minimum distance possible for all the intermediate nodes, right? Fine. In fact, this is why we call it dynamic programming, because dynamic programming's properties, it must have an overlap, right? So the overlap you're seeing over here, that if I have to do it on this particular primary array, right, for primary matrix, then I would calculate the minimum distance for A again while calculating the minimum distance for B, because here I have to do it for both A and B. But while calculating this matrix, I already did it once for A. So why again I would do it for A when I am doing it for B in this place, right? So rather I could directly use this matrix. This is where the overlap happens. And that's why we say it's a dynamic programming approach. Anyways, so now let's do that. Same steps. So A to A, 0. A to B, everything remains same, because now,
No, sir.
no, sorry,
Not-
sorry. Yeah, there is a difference. Okay. Yeah. So A to B, when I'm going A to B, so I can, anyway, A or B is the pit stop. So I can go -2. There is no point. A to C, when I'm going, what can I do? I can use B as an intermediate, A to B and B to C, right? Because B can serve, in fact, I would only check B as an intermediate on this particular matrix. Fine. So check B, again I'm repeating, only check B as an intermediate, but do your task on this matrix. You don't have to check for A, right? So A to B and then B to C. While filling up this particular position, I would do. So what is A to B here? -2. What is B to C over here? 3. What is this value? 1. Right? And what was the previous distance between A to C? Infinity. Whichever is less, 1 is less. So pick 1. So what does this mean? That means I can go from A to C by using B as an intermediate. That means I can use a 2-length path, right, in order to go from A to C, whose length is 1, by having B as an intermediate step. Right? In this case, I could not use B as an intermediate, because here I can only use A as an intermediate, and that's why I could not reach C. But here I could reach C. So therefore it becomes 1. Fine. So, okay, now A to D, let's do that. A to D was infinity over here, right? Again, A to B as an intermediate, and then B to D. So what is A to B over here? Same thing, -2. And what is B to D over here? B to D is 2. What is this? 0. What was the initial distance between A to D? A to D was infinity. So which one is less? 0 is less. So 0. So what does this mean? That I can move from A to D by traveling a path with 0. So -2 plus 2, 0. How many of you did not get that? You can ask if I can repeat, because this is the last iteration I'm doing. So if you have doubt, you can ask.
So basically, like in each iteration, we take the distance matrix from the previous iteration and only check for the current vertex, like current
Current
additional
vertex.
vertex.
Correct. So when you go for A3, right? So what does that 3 means? That means you can use A or B or C as your intermediate vertex. That's the meaning. But how will you actually solve it? You would consider A3, that is, you would calculate A3 by only using C as an intermediate vertex and by checking all the distance value from A2. You don't have to worry about A or B.
Yeah, because they have already been taken care of in the
Already been
previous.
taken care. Exactly. That is the part where that's why we can call it dynamic programming. That overlapping is happening in these matrices, right?
Okay.
So can you
But the meaning is that A or B or C. Okay.
Exactly. The idea is that,
Okay, sir.
right? So if you were doing it on this A0 matrix now, you can calculate A3 directly from A0 also. But if you do it on A0, then you have to calculate using A as intermediate, B as intermediate, and C as intermediate and find the minimum between them. And in fact, that is this equation. Just see what this equation is doing. Minimum among all K. So here you have to actually do using A as intermediate, B
The
as
minimum among all the three we have to consider, right? All the previous two
minimum
matrix
among
we have
all
to
the three you have to consider, but while you are solving the problem, right? So you can only do it with respect to the previous. So when I'm calculating A3, calculate from A2 all the values by using only C as the intermediate step. That's what I showed you just when I'm calculating A2. The idea is I can take both A and B as intermediate, but I would not take A as an intermediate option. I would only take B as an intermediate option as long as I'm taking the values from A1 and not from A0, right? So always when you calculate A of 2, take the values of A of 1 and consider only B as intermediate. When you consider A3, when you fill up A3, take the values whatever is there in A2 and consider only C as intermediate. Don't bother about A or B.
Sir, how are we taking this intermediate, sir? Sorry, I was lost.
Yeah, intermediate this. So that's how I'm filling it up, right? So A to B, let's say A to B I have to reach, right? So what value I would put here? That's my concern. What is the intermediate in this case? Only B I would take as intermediate, right? And on which matrix I would perform? This matrix I would take the distances. So what I would do is when I have to fill up A to B, that is this box, right? I would consider I can go from, oh sorry, not A to B, A to C. A to B so anyway. So what I mean is when I have to fill up A to C, right? A to B is I'm using B as intermediate and destination is B doesn't make sense. What I mean is A to C. So what does that mean? I'm going from A to the intermediate node. What is the intermediate node? B. So I'm going from A to B and then I would go from B to C because that's what my distance is, A to C.
So sir, this intermediate we have to check from the graph, right?
From the previous matrix, this matrix that you build up just before that, right? So now you check A to B. What is A to B in this matrix? A to B is -2.
-2.
Put -2. What is B to C in the previous this matrix? B to C is 3. So put 3. So what is this? -2 plus 3 is 1.
1, okay.
Right? Now what was A to C initially? Actually, what are you doing? You're moving from A to C. So A to C was infinity. So 1 or infinity, whichever is minimum you would consider, right? You're finding minimum distance. So take 1, put it in AC. That's why we have put 1 here.
Right? So why it is K minus 1?
Where is K minus 1? This one?
Right. Yeah, why it is K minus, why it is not K?
Because you are considering up to K minus 1 vertices, right? You cannot consider Kth vertex.
Understood. That is a number, right? I was thinking like K is the intermediate vertex.
No.
It is a number.
It's a number, yeah. So that's why I wrote here it is 0 to K minus 1. I am taking an example of ABCD. Don't get confused in that, yeah.
Okay.
Fine. So 0, -2, 1, 0. Let's complete this. So now B to A using B as intermediate doesn't make any sense. So let's put the same value that I cannot reach from B to A, infinity. B to B is 0. B to C. Now, when I'm writing B to C, what does that mean? Again, B is the intermediate, doesn't make any difference. So B to C would be 3. B to D would be 2. because B itself is the intermediate node. If my source is itself the intermediate node, then I don't have any option. So now there would be some, hopefully some changes. So let's see. C2A. The next iteration is for C2A. So C2B I would go because this is the B is the intermediate. So C2B, B2A. So what is C2B in this graph? C2B is infinity. So this answer would be whatever you put, it is infinity. What was my initial C2B? Sorry, C2A,
Infinity.
C2 infinity. So anyways, I cannot go to infinity. Okay. So C2B, next thing. C2B, B is the intermediate itself, so doesn't make any change. So it's infinity. C2C, C2C, 0. C2D, if I have to go. So C2D, sorry, C2B, B2D, right? What is C2B? Anyway, again infinity. So this is infinity. C2B is infinity, right? Sorry, this one. C2B is infinity. So you got infinity. So this does not make any difference. Let's say next. Now let's D. So D to B, B to A. Fine. What is D to B? D to B is 2. D to B is 2. What is B to A? B to A is infinity. So this is infinity.
Infinity.
What was my D to A initially in this graph? 4. Right? So 4 was my initial value. So 4 is the minimum. So do not change it. Keep it 4. So that means what? I have already converged my path, that I can directly go from D to A by using a single length path, which is 4. So whenever I'm trying to find a larger length path, in order, larger, the larger number of edge path, what I'm encountering is the value is much more. So that means I have a direct connection. It has converged. So D to A is 4. Okay. So now next thing is D to B. So D to B is anyway, the B is the intermediate node. So whatever it was, infinity.
No, 2.
No, I have to go from D to B.
B is intermediate.
Right? And no, not D is intermediate.
B, I said B.
Yeah, B is intermediate. And then what is the destination in this place? B itself, right?
B itself, yeah.
So it doesn't make any difference. I have to go from D to, it will be whatever was earlier, that is 2.
2.
But just a minute, why did I, 2, yeah.
Yes, 2, sir.
2. Fine. So now D to C. Please keep this thing in mind. I'm repeating again. Floyd-Warshall algorithm, always consider the last vertex. In this case, when I'm at 2, consider B as the intermediate option. When I'm at 1, consider A as the intermediate option. When I would be at 3, consider C as the only intermediate. Okay. But you don't have to take A and B as intermediate while calculating. Only consider C as intermediate. Very important point is, when you consider only C as intermediate, do the distance calculation from this matrix, just the previous matrix, and not from this one, neither from this one, and not from the graph. Calculate the distance. When I'm calculating this A2 graph, right? A2 matrix, I'm always taking the distance, looking back to this A1 matrix, right? When I calculated A1 matrix, I looked back, I used A as the intermediate and this. So let's say I write some alpha to A as the intermediate and A to beta. So I wrote this alpha to A distance and A to beta distance from this matrix. Right? So always consider these intermediate distances from the previous matrix and always consider the current node only as the intermediate. So current means in case of 1, just A, in case of 2, the B, in case of 3, C, right? Internally keep in your mind that we are considering A or B or C. And that is taken care of when you are using just the previous matrix. If you use the root matrix or the main matrix, the adjacency matrix, then you have to do this A or B or C individually and take the minimum. But you don't have to worry about that as long as you are using just the previous matrix. You can only take the current node which you are considering, the latest node as the intermediate, right? AC. Okay, so now D to C, so D to B, B to C. What is D to B? In this matrix, you would see D to B is 2, B to C is 3.
2 plus 3, 5.
5. What was the initial value of D to C? D to C
5.
was 5. So doesn't make any
No change.
difference. Keep it 5. Right? Okay. So I can go from, by the way, okay. So, by the way, so what is the difference between these two 5? What is the meaning of this 5? And what is the meaning of this 5 that I got here?
So the last one is when you take the part D, A, B, C. The first one is when you directly go to C.
Exactly. Thanks. So when I take the path D, A, B, C, and this means when I take the path DC, I mean from D to C, DC. Even this one is DC because this is the adjacency list only. Right? So now you see the beauty of it is when we told that when I'm at A2, that means I'm considering both A, that A or B or both. That's what I told, right? See, you are only taking B as the intermediate. But the path that you got here, 5, right? Which can actually, I can write this 5 is same as this 5. So I can put, I can travel using this path or this path, whatever. Both of them are 5. So that is fine. So see, the beauty is I only considered B as the intermediate while calculating this matrix, but I got this DABC path. So A is actually being incorporated. That's why I'm saying, because you calculated the values of this matrix depending upon the values of this matrix, which considered A as the intermediate while calculating this matrix. That's why when you are considering this matrix, by taking the values from this matrix, having A as an option for intermediate vertex is implicitly taken care of. Right? That's why you got this DABC path. Otherwise, you would have got only path having intermediate node as B. But here you got both A and B as the possible two intermediate nodes. And still you get the minimum path, which is 5. Right? So anyways, so this 5 is corresponding to DABC path. This 5 is corresponding to the DC edge. Both are fine. Anyone you can consider. And then D to D, it's 0. Fine. So I would not repeat one more step. You can do that if you want. So A3, you would only consider which as the intermediate node, C as the intermediate node. And you would take the distances from this. So for every, while filling up every I, j index position, you would consider I to C and C to J and put the IC value from this matrix and CJ value from this matrix and consider the whatever, sum it up. And let's say you got an alpha as the summation. So consider this alpha with the IJ value in this matrix, right? IJ index position in this matrix. Whichever is minimum, take that.
So sir, how long we will go this?
Tell me how long. So what is this? What does this 2 mean? That you are considering A or B as intermediate.
Yes.
1 means you are considering A as intermediate. 3 means you are considering A or B or C as intermediate. So that means what? You have 4 vertices.
So
that's
A4,
it. You consider till A4 and that's it.
Till A4. Okay.
Yeah. What would A4 means? By considering D as the intermediate vertex. And you would calculate A4 by using the matrix values from this matrix, A3. Right? Now, we are explaining it and then discussing. That's why it is taking time. Otherwise, it would be very fast. You wouldn't need much time. Right?
And so this number is proportional to the number of vertices in a graph, right?
Not proportional, exactly. Exactly.
Okay.
Yeah.
Okay.
Because that's how it is working, right? I am considering each node as a probable intermediate step. Right?
Yeah.
So you have to, in order to incorporate all the possible paths, you have to take care of all the intermediate possible nodes, right? So that's why I'm running it for n times.
Okay.
So what do we finally tell? Because we have done through all the nodes, and each distance is a different value.
So yeah. So what does that mean?
Minimum of all the. There's no single value to compare between the intermediate nodes, no.
Yeah, so what is happening here is you're finding the minimum path between all possible pairs of vertices and considering any length path. At each level, you are considering, so let's say here I am only considering it's a adjacency matrix, so it only considers a direct length, the direct edge. Here I mean I'm considering A as the intermediate node, what are the possible minimum length path that can be there, right? So here I'm considering having A or B both as intermediate node. How can I reach from I to J having A and B both as possible intermediate node? When I'm at A3, that would mean having A, B, C, all three of them, or any one of, so basically among
No,
A or, yeah,
no,
as,
what I meant to ask the question now, which is advantageous to go from A from A through B, or A through B or C, or A through B or C and D, which is advantageous?
whichever is the minimum.
Sessions we can make.
Sorry, I didn't get the question. Whichever path is minimum, that's where you will go.
No, it's always not minimum everywhere, no?
No,
Is
no.
it progressively decreasing or no?
No, if you want to go from A to which node you want to go? So let's say tell me the node where you want to go from A.
A to D.
A to D we want to go, right? So at first you have to check how many paths are there. Is there multiple path or is there only one path? So you can use A to B and B to D you can go, right? So what does that mean?
Taking a multiple path is our option only, no? So you can take it or you can just not to take it, is it?
Yeah.
Or it's a mandatory requirement that I got to really explore all the multiple paths, then you decide about that.
No, see, what is the motivation of Floyd-Warshall algorithm? The thing is we are trying to find the minimum path length. If it considers
Minimum
three,
path length.
that's it. So obviously the minimum would be one distinct path only. How can the minimum maybe 4 or 5 path? Minimum, it can be, by the way.
No. Minimum will be one only, but I cannot decide about that is the minimum unless I finish all my explorations, no? A and AB and ABC and ABD, I have to finish it among all the things, then I have to take the minimum of all the
Correct.
things, no?
Correct.
So there's always I got to explore all the options.
Yeah. So
Yes.
Otherwise, how will you get? If you want to find only a single pair shortest path, that is, let's say you want to only find minimum between A and D, and you are not worrying about anything else, right? So then you would go for single source shortest path. That is your Dijkstra's algorithm. Why the idea of using Floyd-Warshall is I want to find the minimum path between all possible pair of vertices. That's why it is called all pairs shortest path.
So we have to take all the possible pairs which are going from A to D path, right?
Yeah.
Okay.
So can we do within the short time of the exam?
Yes. This would see. I am explaining this graph like this. What do you have to do? You have to just, this is adjacency matrix. After that, while calculating A1, right? What you have to do is just consider A as my intermediate vertex. So every time you see, let's say I'm filling CD, right? When you fill up this particular position corresponding to CD.
Okay.
So you have to use C to A to D. Just check the value of C to A and A to D over here in the previous matrix. C to A is infinity. So anyways, the value is infinity. So what was the initial value of C to D, right? Initial value was also infinity. So it doesn't matter. So let's say this initial value was alpha something, right? So you calculate this C to A to D, calculate this thing as beta, check the value if it is, let's say this value as alpha, and you take the minimum between alpha and beta and put it over here, C to D. Right. So
suppose if I'm getting A to D 0 somewhere in the intermediate stage without me completing A, B, C, D, can I stop there and declare that A to D is 0?
A to D as 0 means you can, it can again further get reduced if your graph has negative edges, then it might get reduced further. Like here A to B is -2, right? See.
No, A to D we are talking about.
Okay,
So
I got it. But let's say you cannot guarantee that. Let's say there can be a path using which you can go from A to D in a lesser length. Let's say in less length than 0.
okay. So we cannot stop in between.
No, no, no. You're stopping in between. So have this idea. I mean, if you don't have the conceptual intuition, then these doubts would come. The main problem is I'm trying to use as many possible intermediate steps between given two pair of points. Now there can be a situation in which a path with more intermediate vertices is actually of overall lesser length, but a path with more intermediate, a lesser intermediate vertex, or let's say a direct edge, might be of greater length. Why? Because there can be negative edges, right? Now, if that is the scenario, I cannot stop in between. In order to find the minimum path, I have to always consider all the possible intermediate vertices, and that would only happen when I consider all the vertices. I go up to A of n. Okay. Yeah.
Okay, sir. Thank you.
And it wouldn't take more time if you practice it. It would, if I do it screen without explaining, it would take hardly 1 minute, not more than that.
So, sir, in the last final answer will be the minimum of all the vertices, right? I mean, of the all the matrices,
All
which
the
is
yeah,
yeah,
all the paths, all 1 length, 2
all the
length, 3
paths,
length, yeah.
4 length up to
4 length we actually don't need here, because I don't think we have a cycle. Only 4 vertices are there, so
4
3.
vertices. So
So what, 3 is the maximum
three
path
path
length,
length. Yeah.
right? So I have
Sir?
only, yeah.
Sir, can you please explain this statement one more, sir? That minimum of A to I to K minus 1 comma K minus
Fine.
this one, sir.
Yeah. So did you understand this matrix part?
Yes, sir. Yes, sir.
Got it, right? Just we would tally it with that. Let me just clean it up a little bit. Okay, so let's see this. So what is this K? K is basically the number of nodes that I'm taking as intermediate. Now, when I'm taking ijk, what does this mean? I'm trying to fill up the matrix ij position by considering k vertices, right? Up to that k vertices means what? How many vertices? K vertices. So essentially, if I ask you which vertices, that would be 0 to k minus 1, right? So 0 to k minus 1 vertices I would use as possible intermediate steps between source I and destination j. That is what aijk means. Is that okay? Is this definition okay?
Yes, sir.
Fine.
So we can.
0 is the direct edge, sir. 0 is the direct
Sorry,
one, sir.
0
is
is
the direct one.
0 is the direct one, where you are not using any, basically any vertices. Yeah.
Any other edges.
So can we say K is like the power of A in the matrix one? Like
Exactly.
I
Yeah,
think yes, it
correct.
is.
You can tell that. Actually, that is the case. So let's come to that. Okay, fine. So that is done. So now let's come to minimum of k. What is this minimum of k means? In this example, when we filled up the matrix, what did we do? for every ij, for filling up every ij position in this matrix, we did I to B, B to J, right? And on which matrix did we calculate this I to B distance and B to J distance from? From
A1.
A. So you, while calculating A2, you are taking the distance from A1. While calculating K, you are taking the distance from K minus 1. Is it telling? While doing it for 2, you are using it for 1 from this matrix.
Yeah.
That's what K, that's why here it is K minus 1. Okay? Okay, fine. Now, what did we do? We use I to B and B to J. Now the thing is, here while filling up these matrices, the shortcut trick is not shortcut. I mean, the conceptual thing is you always use just the previous matrix so that you don't have to worry about A. You can only take the B as intermediate and calculate the distances from this matrix so that you don't have to worry about A. While you do it for A3, you can only, while filling up ij position in A3, all you have to do is do I to C, C to J, and calculate that I to C distance and C to J distance from this matrix, so that you don't have to worry about neither A nor B. Right? So this is how we, in pen and paper mode, we do it. For the sake of convenience, we just take the previous matrix and do it on C.
But
But
sir, we also consider A or B, right? I mean,
But we
although we
internally,
are,
exactly,
yeah,
but internally, this matrix takes care of the A and B case, right? I mean, the A
yes,
case. But that
Okay.
is how we, pen and paper we are solving. But when you are
So, sir,
writing the code, you have to, just a
uh,
second, Pranjal. So when you are writing the code, you have to mention it, right? Because that is been taken care of. So what is happening? If I have to do it for A, B, or C, what was our main concern? That I would do it for A as intermediate, B as intermediate, C as intermediate, and find the minimum among them. Correct? So which actually, if I do it on A0, I have to do it on A, B, and C, 3 possible intermediates. So I to C, I to B, J, I to A, J. And then I would find the minimum among them. That's what our main idea was. Right? So now see, that's why here, this is what's happening over here. I would consider minimum over K. That is all the possible K I would consider. Like here I'm considering for A, B, C. Here I would consider for A and B. Here it is a single A, doesn't matter. So in the iteration here, I would consider for all the possible thing and I would take the minimum. So that's why we are writing this minimum. But while solving problem, I can just use the previous matrix and I don't have to worry about this A and B, and I can only take C as the intermediate. So, but this notation has to mention, right? Because I have to actually find the minimum among all the possible intermediates that I got. That's why this minimum. And obviously this is, I don't think I have to tell this, because we are moving from I to K minus 1. Why K minus 1? Because every time when you are at, let's say, index K, we are using the last as the intermediate over here, right? So you are moving from your so at index K, while doing it for AK, you are moving from I to K minus 1, then you are moving from K minus 1 to J, right? So that's why you are writing I to K minus 1 and K minus 1 to J. So this is essentially as I to same. This is basically means I to C, C to J, while calculating for A3. Right? If you understood this matrix fill up thing, then this thing would be very safe. Now, again,
So that K minus 1 is the index.
K minus
yeah,
1
so
is the
that's
index.
why,
Yeah.
yeah, that's what I was asking. Okay, sir, yeah, got it now.
Is the index.
Yeah. Okay.
And again, so while we calculated the path, let's say I calculated I to some B in this matrix, right? When I'm filling up, no, so sorry, in this matrix. B is in this matrix. When I'm filling up this matrix, I calculated I to B and B to J. And let's say I got some alpha as the distance. But I already saw that ijth position, the ijth position in my A1. This is when I'm doing while calculating A2, because B intermediate is happening in A2, right? So I used I to B, B to J, I got alpha, right? And but in A1, direct I to J is suppose some beta. I mean, sum over here, I to j was beta. So the I to b in A1 I took, and b to j also from A1 I took, and I got the summation as alpha. But from A1 I to j I got beta. Direct I to j also beta was there. And then I considered the minimum among them, right? And whichever is the minimum, that value I put in this matrix at the ij position. So I have to consider the scenario when already in the previous matrix, the value which was there is actually lesser than the value if I use intermediate. So many situation happened while I was filling up this matrix, right? We saw that previous value was lesser, so keep it. So yeah, I remember this while filling up 4.
Yeah,
I think I got
it
something
was
more than,
same.
yeah, it was yeah, something, I think yeah, whatever it is,
It was
it
same,
was
I think.
the same. Fine.
Yeah.
So we got that value. So I have to consider the situation where I am getting previous value which was already there, that is lesser, or that may be same, whatever. Same is okay, but if it is lesser, then I have to consider the lesser value only. Correct. So I have to take care of that. That's why we are using minimum of this whole thing, whichever is minimum. This I took that intermediate. This is your intermediate, right? This is your intermediate. This I to intermediate and intermediate to destination, or the ijth, this ijth, in where while filling up for A2, I check the ijth for A1 if that is minimum. So while filling up of A of k, I have to check the intermediate of A of k minus 1 ij. So minimum A of k minus 1 ij. If this is minimum, or if this is minimum, whichever is minimum, I would take that. Is the meaning okay now?
Yes.
Yes, sir.
Fine. And that's it. All you have to do is in the code. Now I don't think you would have any problem in the code also, because if you understood this recurrence, all you have to do is put 3 loops and run ijk. That's it. All you have to do is put 3 loops, and for I in range, for j in range, for k in range. That's it. And put this equation and it works. So other than that, there is nothing in the code also. So Floyd Warshall is okay?
Yes.
Don't worry if
Yes,
you
sir.
feel that this filling up this matrices is taking time. Believe me, if you do it on your own, it would not take your time. I'm
If
doing
there
it
are
on.
more vertices, then I think it will
It would not come.
slightly
Yeah, it would
take
not
more
come.
time.
Yeah. Obviously, that would happen. But in exams, if we are asking you this kind of Floyd Warshall or some this matrix fill up question, it would not come for more than 4 or let's say even if it comes for 5 vertex, the number of edges would be lesser. You don't have to consider many cases. But more than 5 vertex would never come. Anyway, so Floyd Warshall is done. Bellman-Ford also I discussed. Dijkstra also. So I briefly discussed.
So,
Now, yeah.
what was the complexity of Bellman-Ford?
Bellman-Ford, what did we do? Here I wrote, right? Yeah. So outer for loop running for order n times, right? N minus 1, n, whatever you want to order n times. And here inside the for loop, you are having for all the edges.
Okay, and because okay, so edges will
Yeah.
give
Order
the
is,
square.
it is m, edges is n,
M
and
times n.
this is n. But m can be n square when it's nearly a complex, complete graph.
Yeah.
Right? Why? Because n choose 2 is the number of edges, which is n into n minus 1 by 2, which is actually equal to, so this is n square into n, which is n cube. And if you do not use an adjacency list, so if I use an adjacency matrix, so I have to change this for loop with what? 2 for loops, because that's an adjacency matrix. So for I in range, for j in range, column, row. So therefore n square. Anyway, this still becomes n square. So this is n square, and n, that's why we got n cube. So adjacency matrix, if you use, it would take n cube time. Adjacency list, if you use, it would take m into n time. Now, if your adjacency list that you use is actually working on a complete or nearly complete graph, then that there is no difference or there is no optimization or efficiency gained by using adjacency list. I think these were discussed in the initial weeks that too.
Yes, sir.
right? When you have a complete graph or nearly complete graph, it is better to work with arrays rather than list. But when you have a sparse kind of graph, a list gives us much benefit, because when it is a sparse graph, this m would be not be in order in square. It would be much lesser than that, right? So yeah.
So in that case, like, i- isn't Floyd virtual a more beneficial algorithm because it will give the paths from every node to another node in the same amount of time?
Yeah, you can tell it in that manner. Yeah, correct. If the graph is a sparse graph, you can apply Floyd Warshall in the same amount of time. It would give you all possible paths. So you are getting, I mean, but you have to have the requirement to have all possible pair of paths, right? But let's say your problem statement is asking you that the source is fixed. So you are trying to find out, let's say, the minimum distance a Zomato delivery guy has to go. Not Zomato. Zomato is not a proper example. So let's fix a particular shop, right? So let's say some shop delivers some product to different homes, different does home delivery. So that shop is destination that sorry, the source is fixed always. So in that case, you need not run a all pair shortest path algorithm on the graph or on the city graph that you got, because you don't need to find shortest distance between random two houses. Those two houses would be two nodes in the graph, right? I always need to find the shortest distance from my shop to all possible, to all the houses. So that Dijkstra does perfectly fine. So you can go for Dijkstra. So, yeah, but yeah, your idea is correct. You can apply Floyd Warshall and it would give you lesser time if the graph is kind of.
So basically, each row in the Floyd virtual is like a separate Bellman code. Can we say that?
At the end, correct. Yeah, at a of k.
Yes, sir.
Correct.
Okay, sir.
By the way, one more important point. So since you mentioned this, nice. If Bellman-Ford can detect negative weighted cycle, but can Floyd Warshall detect negative weighted cycle? I think one graded question is there like this.
Yes, sir, it can.
And how?
Yes, sir.
So if any of like the diagonal entries is negative,
And why will it happen? Can you briefly tell?
if the only possible way for it to become negative is when it comes, like, it's coming back to the same point. So that means it has to go through a negative cycle, and
Correct.
zero is the initial case. So if it goes below zero, then that means it has gone through a negative cycle.
Exactly. So even if in this graph, if you would have, let's say, changed this 2 to -6, no, let's say -8, right? So if you had something like this, then you would see a change happening, right? Because this whole cycle, A, B, D, the net is -2. So if you now run the Floyd Warshall algorithm, you would see that I would get the diagonal element value as -2, right? That is, I can reach from A to A in -2 distance.
At which point? Which vertex?
When you consider, so what are the vertices you are considering? You are considering A, B, D, and then coming back to A, right? So that means what? B is an intermediate in the path.
Yeah.
D is an intermediate in the path. So if D is an intermediate in the path where you will get this -2 value, that means what? At A of 4, you would get this thing, right? Because you have to consider D as the intermediate. So D intermediate would only be considered at A of 4 matrix while you calculate A of 4. So when you calculate A of 4, you would see that you take D as an intermediate and you fill up A to A. Then that means what? You want to go from A to D. You would write, I want to go from A to D and then I want to go from D to A. Right? So that would be possible, that you can go from A to D via B. Right? Via B would happen. This is -8, right? -8. So this via B would happen, then B to D would happen, and then D to A would happen. This is -8 plus 2 plus 4. Total would be -2. This -2 would come in your A4. While you calculate A4, you would get the A to A matrix value here over as -2. Right? So Floyd Warshall algorithm can also calculate negative weighted cycle when this A of I comma I, any for all I, not for any I, for any I or not in element of you guys did this element all and I, this thing, this science in any subject you did, right?
Max, I think.
Yeah. So fine. So for there exists some, for there must at least exist one I, where I is an element of your 0 to n minus 1.
N minus 1.
Yeah. 0 to n minus 1, such that a of I is equal to, or let's say a of I is less than 0. If this is the case, then you can tell that I have a negative weighted cycle.
This is basically diagonal.
Yeah,
Diagonal element.
diagonal elements.
Sorry, maybe it happens at the third iteration or whatever iteration it will be. We'll just say that it has negative cycle.
Whichever iteration it happens, you can say it's a negative weighted cycle.
Yeah.
Right. But you don't have to think about whichever iteration, because at the end of the day, when you are in your algorithm has terminated, you do it for n vertices, right? At an, at that level, I mean, if there is a negative weighted cycle in let's say some in between iteration, then also the negative value would be there in your matrix till the end. So even by checking the last matrix, you can tell that.
But it will increase, right? I mean, if it was in the previous iteration, it was -1, then in the next
it would increase.
Might become -3. And
might become -3. It would only become -3.
It will decrease, sir, because -1 is greater
sorry,
than
yeah.
-3.
I mean, yeah, correct. Decrease. I mean,
yeah,
the negative value would increase. That was the idea.
Yeah.
Right?
Negative value.
Yeah. So, but one trick is there. Okay, anyways, so much difficulty wouldn't come in the exam. But the thing is that can only happen when the shorter negative weight cycle is actually a part of a larger negative weight cycle. Because unless and until you have another intermediate node, a part of that negative weighted cycle, the value would not further decrease. It would remain constant. Don't worry about that. If you did not get that, these things would happen.
Complex.
Sir, so basically, the diagonal value should be 0, should not should not be less than 0.
That's it. Bas. Yeah. That can be a bottom line. If it is less than 0 at any point, there is a negative weighted cycle. So the whole point is Floyd-Warshall algorithm can detect negative weighted cycle just like Bellman-Ford algorithm. Okay.
Okay. Sir, just one more
Can you
thing.
please read that statement, sir? Can you please read,
Sorry?
read the statement? There exists I that belongs to a minus n minus 1. That statement.
Yeah.
Can you read that one? Because the notations are something new.
Okay, no problem. No problem. What I mean is, okay, forget about the notation. What I mean is, in the matrix, after the Floyd-Warshall algorithm has terminated, if any of the diagonal element, any of the primary diagonal element, so II means what? II means all the left diagonal elements, right?
Yeah.
So any one or more of the left diagonal element, if it is negative, then there is a negative weighted cycle.
Okay.
That's it, right? Yeah.
Okay.
Sir, just one more thing. In the beginning of the session, we were talking about Dijkstra algorithm and the negative weights. So, sir, in the exam, if the question is asked, like, can we work with the negative weights and Dijkstra algorithm? So, what would be the answer? Like, no, right? We can't use.
If the question, so you have to be a little bit specific about the statement, which it is what it is saying. So let's say if the question states that if a graph has negative weighted edges, will Dijkstra algorithm always work? So then you would say no. Will Dijkstra algorithm never work? Then you would say no, it is false, because the main idea is, keep in mind, Dijkstra algorithm may or may not work. That's, if you keep that thing in mind, whatever statement comes, you would be able to answer. And if a graph has been given to you, then you have to check it out and tell.
Okay.
Right.
Okay. So we are talking about negative weights, not negative cycle.
Not negative. Negative cycle means there is no notion of shortest path.
Yeah.
In any of the graph, right?
In any of algorithm, any graph, anything. Because see, so I think many people tell it that, yeah, if it is a negative weighted cycle, then Bellman-Ford and Floyd-Warshall algorithm can find the shortest distance. No, that's not a correct way to answer it. If there is a negative weighted cycle, the notion of negative path does not exist, because you can go up to -infinity. Only thing is, Bellman-Ford and Floyd-Warshall algorithm can detect the presence of a negative weighted cycle. It cannot calculate it cannot calculate shortest path as long as there is a negative weighted cycle in the graph. Right? So that, just keep that thing in your mind.
Okay, so sir, even in Dijkstra also, if we have negative weights, so if that negative weight does not interfere with the greedy approach of Dijkstra, then it will give us the shortest path.
Exactly.
But if it does, then it won't.
Exactly. And as a hint to your question, just try out the mock Dijkstra graph question that has been given. Apply
Okay.
Dijkstra, check whether it is giving you shortest distance or not. It would, as much as I remember, it would give you the correct answer, but it has negative weights edges.
Okay, sir. So if the questions come, the answer should be may or may not.
May or may not, and if the question comes in a statement format, just have this idea in your mind, and whatever, I mean, then you can answer that, right?
Okay, sir.
That it may or
Thank
may
you, sir.
not. Yeah. So anyone having doubt with Dijkstra, by the way, there is no problem. If you have doubt, you can ask. Problem solving, code discussion, I can do it later.
Can you take that mock example?
The mock example deadline is tomorrow, right?
Ah, okay.
Anyways,
I have solved a bit, but I wasn't confident.
fine, no problem.
So mock exam tomorrow, but will you be discussing the mock exam sometime?
I can discuss it now, but I don't want to discuss all the question. If you have
Not all
specific,
yeah,
specific
like
questions,
Dijkstra.
I would discuss. So, but before going into that, any other topics? And week 6 is left, so I would like to finish up the topic discussions at first. With respect, more stress on problem solving. So,
Yes,
I
sir.
think,
So please wind up the topic first.
yeah,
It will
I
be.
think Prim's algorithm. Someone said, right? How to solve Prim's.
Yes.
So let's take an example. I think one example of Prim's was there in the.
Sir, how to identify which algorithm to deploy based on the problem statement? If the problem statement is silent on,
That's the whole idea of PDSA course.
yeah, oh, right, no, but
Uh,
you cannot
but
answer it.
yeah, maybe you can be a little bit specific. I would be able to understand that. What do you mean? That can you tell me in terms of any specific type of problem or? Okay, Prims is not there.
No, it's not.
Fine, no worries. So let's take.
An graded question. Yeah.
By the way, I think this is that Floyd-Warshall question. I think this is fine. Right. So this is kind of a graph over here. Let me.
Kruskal's. Yeah.
This is Kruskal's, but anyway, I would do Prims on it.
Okay.
Just a minute. Fine. So let's say this is a graph, and I have to apply Prims on starting from which node? Tell me any one node.
A.
A. Okay. If you are messaging, I would request you to directly unmute and tell, because I wouldn't be
Hello.
able to see you. Yeah.
Yeah, A, sir.
Yeah, A, right? Okay. Fine. So let's do it on A. So how prims would work? The idea of prims algo is that you start from a source vertex, not source in the sense in MST, I don't have to call it a source. In fact, Kruskal does not take any source. It picks up minimum length edges according to in that order. But Prince would actually prefer to start from a particular node, and it would go on building up the MST from that node. So what is the idea of Prim's algorithm? So I am starting from A. So starting from A. From any one node you can start. It doesn't make a difference. Even if you start from D or F or E or C, whatever node, it would give you the minimum spanning tree only. It might give you a different minimum spanning tree, but why I am saying different minimum spanning tree? In this graph, I can have multiple minimum spanning tree. And why is it so?
Because the edges are
Because edges
Duplicate.
are different.
Edges are duplicate.
Duplicate
Yeah,
edges are there.
and the
Same
weight are
value.
duplicate.
Exactly. Same value edges are there. So that's why I can have a different minimum spanning tree with the same minimum weight. But if I would have had a single, all the edge weights were distinct, then I can always guarantee from whichever node you start, I would get the common minimum spanning tree, right? Okay, so starting from A, how it would work is, you start from A, you see what are the neighboring nodes of A, and you pick up the minimum one. So I would take A now, right? Let's take another color. I would take A, and I would pick the vertex with the minimum value, which is a neighbor of A. So what are the neighbors of A? B is a neighbor of A,
B,
C is a neighbor of A,
C,
1, but here I have 1 which is minimum, so I would pick B.
B.
So this is the MST. This is my MST that I'm constructing now. So A to B is done. Now the thing is, what you are actually doing is in heap. So this is, even if you have not understood the heap implementation, it's in week 6. But anyways, what we are internally doing is in the heap, we would push all the neighboring nodes of A, and then we would do the extract mean. That's how we did this, pick up this minimum value 1. So when we are at A, I would push the neighbors of A in the heap. So I would push B, right, which is 1, and I would push C, which is 6 in the heap, right? And I would do an extract min. So which one would be the extract min at this point? Obviously B is lesser, right?
B1.
So that's why I'm adding A and B, right? So remove this B as of now, because B has been removed. Fine. Okay. Now, so in the heap, C6 is there. Keep that thing in mind. So this is the state of the heap. And okay, don't confuse it with the heap representation that we discussed. I'm just assume that all these values are there in the heap. It's not the heap representation. I'm just showing. Okay, so now when I am at B now, I would push all the neighbors of B in the heap as well, right? So what are the neighbors of B?
C, D, and F.
C, D, and F, correct? So, but this C is C corresponding to 3 value, right? And my F corresponding to 2 value, and D corresponding
D.
to 4 value, correct? These are the nodes now I have picked. Now we again extract min. So every
C.
time you would add the neighbor and do an extract min. So what is the minimum?
F2.
F. Nice. So here F is there, which is a value 2. So remove that. Okay. Next. Now I have reached F, right? So all the neighbors of F I have to push. What are the neighbors of F? D,
D,
1.
E.
E is there, 5. And nothing else, right? Okay.
Nothing else.
Fine. So again extract min. Which one would be there?
D1.
Remove D1. Done. Okay. So now I am at D. So I would push all the neighbors of D. So Acha, one important thing. So now since I have actually moved at D, so this D4 I cannot, I mean, I can remove, right? Because D has already been added, right? So
Yes.
whenever you are pushing something into the heap, and then you check that actually that vertex is visited or not. If it's already been visited, you can just don't consider that.
Mhm.
It's not needed. Okay, so now D is neighbor, E is there with value 3,
A3 and
and
C2.
C value is there with 2. Again, same extract min.
C2.
So D2 C done. Okay. Then all the neighbors of C.
So we can also remove
E4.
C3 and C6.
Sorry.
So we will remove C3 and C6 also.
C6, yeah.
Yeah, correct. Yeah.
Also, so why are we maintaining two E3 and E5? Can't we maintain just E3?
Yeah, you can do that. I mean, if you are pushing, you can check whatever is the minimum, you can keep that only. If it is already there, which is a minimum, but in the heap, you have to check it. See, either while pushing, you can check, but while pushing, you have to search through the heap. That would take more time. Rather than that, if you just maintain a visited dictionary, and whenever you are having the extract min, if check that whether it is already in the MST or not, that would be a constant time check. And even your extract min is login time. So that would be login, overall time would be login. But every time when you pop something out, and if you check that whether corresponding to that vertices are there in the heap or not, you know search time of heap. Search time of heap is order n, right? You cannot search a particular element in a heap. You have to search all the element. So that's why it's better that you make a visited dictionary and check it when you're popping it out, rather than checking all the elements, right? So these are coding, I mean, implementation related thing that
Yes,
would
sir.
come into play. Maybe we can just focus on the problem for this quiz, and then yeah. So, but yeah, question is correct. You can rather do a visited thing than checking every time. So D, C is done. C is never. What
E4.
are C is never? E
C
is there. E4.
E4.
So you push, right? E4, and now you take the extract min, and I have E3 as the only possible. I mean, this is the minimum one, right? So, and that is corresponding to D. That, and since now you have taken E, so you take, every time you push pop the E, you get to E is already visited, so you don't consider E4, you don't consider E5. So this is your MST. So yeah, so then what are the edges? What are the sequence of edges? In Prim's algorithm, the question would come, what are the sequence of edges considered by Prim's algorithm? So AB was the first, then BF was the second, then DF, then DC, right? So that's Prim's algorithm. Now, how much time would Prim's algorithm take? Now, the thing is, if in our code implementation of Prim's algorithm, we saw that what we did was simply using lists and all. So that would take you square time, quadratic time. But if you use binary heap, right? So then it would take you E log V time. Those things are discussed in the open session for Prim's algorithm. You can check that out. Basically, why log v time? Because what you are doing, we were actually doing extract delete min, right? So delete min takes how much time? Log n time, correct? And how many times you are doing delete min? For all the edges, you are doing delete min. Every time you do delete min, you are essentially adding an edge. So that means e times you are using delete min. Delete min takes log n time, and or log v, whatever, log of number of vertices, that time. And how many times you are doing? E times to make the MST. Sorry, I mean for all the edges. So that's why you are going for E log B. For all the possible edges, you are actually doing extract min. So Prim's algorithm is done. Kruskal's algorithm, I don't think we have to discuss. That's just sorting in ascending order and picking up, as long as it is not forming a cycle. Next topic is anything else from week 5? I think everything we anyway covered. So week 6 is left now. Any doubt from week 5? let's go for a 1 or 2 mock question very fast for week 5. Why can I make it smaller? Can I make it somehow smaller? No, right? I mean, so that the graph comes on the screen completely. I don't think so anyways. So let's say this is the graph. Now the question is asking you that how many minimum spanning tree are possible in this graph. So what is the answer? Anyone solved?
So you can press the arrow, left arrow.
Oh yeah, this is there, I think. Yeah, so let's say this is the graph, right? Now my question is, how many number of minimum spanning tree? Number of minimum spanning tree for this graph. First of all, I can see there are repeated edges are there, right? 5, 5, 5 is there. So that means I can have more than one minimum spanning tree. It's not distinct, so I can have more than one. And the question is how many?
So sir, in this minimum, we have to start from any edge, right? And then
yeah,
so start from any vertex. Sorry,
any vertex. Minimum. So Prim's algorithm, Kruskal's algorithm both find minimum spanning tree. But this question is asking you that how many possible minimum spanning trees are there. Right. So if you go by Kruskals or Prim's, that is fine, but it would take you some time and it would not give you all the possible minimum spanning tree. The question is asking you how many possible minimum spanning tree. So the approach would be, see, can you all see my cursor?
yes, yes.
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Fine. So let's see how Kruskals algorithm would work. Okay, how Kruskals would work. So it would pick this 3. This is the minimum value, right? 3. So it would pick this 3 first, this edge. So 2, 5 would be connected. So then what would happen is it would pick the next possible minimum value edge, which is 4, right? 4 is the next possible minimum value edge. So this is connected. While I'm doing it, please keep track of which edges are getting connected. Okay, so 2, 5, this thing is connected now.
3, 6.
This thing is connected now. Okay, done. After that, what would happen?
5.
5. Now, when 5 is coming, then I have multiple choices. Right? I can pick any one of the 5. Before 5, I had only one unique 3 and I had only one unique 4. So there were no options. But now for 5, I have more than one options. When you have more than one option, there can be a chance of having multiple spanning tree. Right?
Yes.
So then you have to carefully consider, okay, so which 5 I would take. So let's proceed with, let's take any one of the 5. Let's say 3, 4. Okay, this 5 I take. Okay, so I take this 5. Fine. What happens after that in the next step? In the next step, I see I can again pick a 5 without forming cycle. Right? If I pick, let's say this 5, will I form cycle? Because this is connected.
No.
This is connected like this. If I take this 5, then this whole thing would get connected without forming any cycle, right? So I can take this 5. So, okay, fine. And again, I can take this 5 also without forming any cycle.
Yeah.
So I had 3 options for 5 and I saw that it doesn't...
All 3 are.
Exactly. So it doesn't matter which edge I pick first and which edge I pick second and which edge I pick third among the 3, 5. All 3 of them would eventually end up in the minimum spanning tree because neither of them are forming cycles. So I don't have to worry about any different minimum spanning tree because all these 5s are there in the spanning tree, right? So you can pick it in different order, but that wouldn't matter because your MST would be the same one. So now you see 1, 4, 3, 2, 5, 6, all these things are connected and that's your MST. So the answer for this question would be what then?
1.
1.
1.
Right? So the answer for this question is 1. You can have only one MST.
So sir, if we take any order in which 5 is there, it doesn't affect the number of minimum spanning tree, right?
As long as any one of in this graph it doesn't affect. The reason for that is because neither of these edges are forming any cycle, because
Cycle.
and none of them, that's why we are not eliminating any one of them. Let's
True.
say this 10 was 5, right? Assume this 10 value between 4 and 6 was 5. Okay.
Yes.
Now you see the problem. Now since 4, 3 and 6, these three were initially connected, right? And when I have, let's say, instead of 1 and 4, this 4 and 6 was 5, suppose. And 1 and 4 was something different. 1 and 4 was something different and 4 and 6 was 5. Now if 4 and 6 was 5, then I can pick this 5, right? After this 5, 4 is there, I can pick this 5. But if I pick this 5, it is forming a cycle. Right? So I cannot act, my Kruskal's algorithm would say that you pick this 5, but I can say that this 5 is forming this cycle. 3, 6, 4 as the cycle. So I cannot pick this 5. So when you cannot pick this 5 weight vertex, then I can also say, okay, what is restricting me? I can either consider this 5, 4, or I can consider this 4, 5. I can eliminate this 5 as well. I can consider this 5. I can consider 4 and 6 being connected together and 3 and 6 being connected together. Because this 10, right?
Any one I have to take. I can't take both.
At that point,
of the 5.
Exactly. So you cannot take both. That means what? But the weight is remaining constant in both cases. 5 plus 4. So that means what? You have 2 possible minimum spanning tree at that point.
Okay.
Right? In one, you would consider this 5 edge. In another, you would consider this 5 edge.
This 5 edge.
Only
without creating a cycle.
Exactly. Only in this particular example, since all the 3 5 weighted edges are part of the same minimum spanning tree, I am not eliminating any one of them. That's why it doesn't matter. That's why there is only one MST.
True. Okay.
So if a graph has same number of edges, then the order of edges does not matter. It does not create another spanning tree.
No. How will it matter? Because anyway, you'd end up with the same MST, right? You are not checking the order of picking up the edges. You are checking what is my MST. That's what the question is asking you. Number of minimum spanning trees.
Got it, sir.
Right. So these kind of MST questions, you have to be a little bit,
tricky, and
tricky.
You have to
be intuitive. You don't have to follow algorithm blindly, because if you follow, you wouldn't be able to answer. It would take more long time. You have to be, you have to just understand these things, that okay, if I'm taking this 5, I'm not eliminating it. That means I am considering all the possible 5 in the same minimum spanning tree. So there would not have, that means I would not have any other option of having another MST, right? Because only other option of MST would come into the action when you have the same weight, but another node to get connected with. And that would only happen when you are actually having 2 edges of equal weight and you are considering any one edge at a time inside an MST, because the other edge would form a cycle, right? Like in this example that I told, that would happen. Fine.
So in short, we don't have to pick those edges which create a cycle and which have a same weight.
Correct. Yeah. I don't think Dijkstra anyone has problem.
G.
Of this question, can someone tell? So what is it saying is, let G be a complete undirected graph on 4 vertices. Right? Let's draw a complete undirected graph on 4 vertices. Okay. Now, having 6 edges, 4 vertices, 6 edges with obviously complete graph, so 6 edges with weights 3, 4, 5, 6, 7, 8. The maximum possible total weight that a minimum spanning tree of G can have. Now, what does this statement means? I have to find the minimum spanning tree of the graph, right? But what can be the maximum possible total weight? So what does that mean is, see this 3, 4, 5, 6, 7, 8, we are not telling which edge is weight what. right? I'm not telling you that where that, yeah.
Where
So
to draw the graph.
correct. I know only 6 edges are there, but I'm not telling you that this is 3, this is 4. I'm not telling that. That is free to you. You can assign the weight in the way you want, but you have to assign the weight in such a manner so that the minimum spanning tree for that graph would have the maximum possible weight among all the MSTs for different assignment of weight at different edges. So I told you that I am allowing you to assign different weights. I mean, these 3, 4, 5, 6, 7, 8 are the edges, weights, right? 3, 4, 5, 6, 7, and 8 are the weights. So this 6 weight you can assign to these 6 edges in any random order. But that's what, and that means you would get that many number of different graphs, right? That many number of different graphs you would get. And among all those different graphs, you have to find the MST for all those different graphs. And then for each of those MST that you got for the different graphs, you have to find the one with the maximum weight. Is the question clear?
So, sir, we can assign these weights to any of the edges in any order, right? I mean, any order means in that order which
in
you
that
see
order,
the.
so that the MST that you get would have the maximum weight.
So we have to like diagonal. We have to give the maximum weight
Why is it so?
because it will connect all the nodes, right? If we connect the diagonal and give the highest weight, like 8 and 7.
Okay, let's do that. If I do 8 here and 7 here, then and after that, where should I put 3, 4, 5, 6? So this node, this edge, what should I put?
Yeah, 3, 4, 5, 6. Like in the remaining, you can put, right?
Any order, 3, 4, 5, 6.
Any order you can put.
Any order? Let's say 3, 4, 5, and 6. Fine. So now if I find the MST of this graph, so first 3 would be taken, so 3. Then 4 would be taken, 4. Then which one? 5 would be taken, 5. Right? So what is the weight? That's it, right? Because all the vertices are covered.
Yeah.
So 6 also.
Why 6?
Okay, it's
MST.
forming a cycle.
I'm forming, yeah, you have to find MST. So what is this? 5, 4, 9, 10, 11, 12. So 12 is the maximum possible weight among all assignments of our graph?
Not really. We will have to check.
Sir, a minimum cost spanning tree, I think, will not have less than this. It cannot have less than 12 weight. It's the least that we can have.
Minimum weight is 12.
Yeah, that is obvious. That is obvious.
The question is very confusing. That's why, because our MST should have a minimum cost. Okay, then they are asking the maximum total
the question
weight.
that's why I was telling
maximum weight.
Understand it in this manner. Given a graph, your minimum spanning tree would have minimum weight among the, I mean, in the graph, right? But have I given you the graph? The question has not given you the graph. The question has told you that you have 4 vertices and 6 edges. And these 3 to 8 are the edge weights. I am not restricting you to assign the edge weights to specific edges. You are free to do that. So if you have 3, 4, 5, 6, 7, 8 as edge weights, and you can assign these edge weights to 6 edges in any random order you want, then essentially you have so many different graphs, right? In one you have some particular, as I mean, the first edge assigned to 3, the third edge assigned to 7, in the second assignment you assign first edge assigned to 8 or something, whatever. You have random assignments and therefore you have different graphs, right?
Okay.
What
I'm thinking is, irrespective of the, they haven't given us edges, irrespective of that, we'll always get 12 as the MST here.
See, understand the question. The thing is, the question is asking you what is the, so okay, just let me complete that. So therefore, for different assignment, you will have different graphs. Now, each of these graph would have its own MST, right? Each of this graph would have its own MST. So you have multiple assignments of these graphs corresponding to different edge weights. Here you have, let's say 8, here the node is 6. here it is 3, the first edge, here it is 4, here it is 8, here it is 3, whatever, right? Different assignments. Now
Sir,
each,
I'm getting that.
yeah, just a minute, I would come to that. Now you MST2, right? Likewise, you would have MST some K,
Some
right?
combinations we have to try.
Right. Now this MST would be the minimum for this, I mean, minimum spanning tree for this particular graph. This MST would be the minimum for this particular graph. The question is asking you, which of this MST would have the maximum weight? For which graph? So for which assignment? In among this 1 to K MSTs, one of the MST would have maximum weight. Let's say this MST has the maximum weight. Suppose this MST has the maximum weight. The question is asking you, what is this graph? What does this graph look like? What is the assignment of the edge weights for this graph? Tell me this graph. Right?
So since the edges are distinct, the MST will always have the same cost, right?
Yes, that's what I'm thinking, sir. In all these graphs, if we try to find the MST, it will always be 12. Whether 3 is on diagonal or on sides, like, or 4 is on whatever, wherever they are, because we always need 3 edges to create a MST. And in that case, 3, 4, 5 will always connect, like will be able to connect regardless of their positions.
If you have distinct edges, you get a distinct MST, right? When I said
Yes, sir.
distinct MST, I mean within that graph. That's the point you are missing. Within this particular assignment of graph, if you have distinct edges, you would have only one distinct MST. You would not have two MSTs. But
Yes,
that
sir.
does not mean that if I change the graph itself, you would not have different MSTs. That is a separate graph. You are changing the edges altogether. So that will have different MSTs.
3, 4, and 5 can form a loop, right?
That's the point. That's the main thing. See.
Oh,
That,
yes, yes,
that
yes.
is the idea, in fact. So
Okay.
think in terms of, you have to form MST, correct? Now you have to maximize the weight. These are the two objectives that you have. I mean, maximize the weight of the MST. Now, how can I do that? Think how Kruskals would work. That's how you form MST, right? So let's think how Kruskals would work.
So is 15 the answer?
Let's see what happens. So how Kruskals would work? To whichever node you apply 3, I mean, sorry, not node, edge. So whichever edge you apply 3, Kruskals would pick that first, right?
Yes, sir.
So irrespective whichever edge you want, just randomly take any edge and assign 3. So let's take whichever edge. Tell me any one edge.
The top edge.
Top edge, this one's fine. So let's assign 3 over here. So assign 3. So Kruskal would pick that at first. After that, what would happen? Kruskal would pick the next minimum one.
That is
Okay,
4.
4. Can I ever create a cycle with 2 edges?
No, sir.
No, sir.
No, sir.
So that guarantees that wherever you put 4, Kruskal would pick 4. Isn't that so? Because Kruskal would only not pick 4 when 4 creates a cycle. But 4 cannot create a cycle because it is the next minimum, only the second minimum edge. So if it is second minimum edge, wherever I put 4, Kruskal would definitely pick 4, irrespective of its position. Right? But
Yes.
see, what I would do is, if I put 3 in this place, I can put 4 over here, or I would put 4 over here. There is a reason for that. In any of these two places, I would put 4. Let's take the left one. Because Kruskal would anyway pick 4. Now, the next minimum is what? 5. Correct? Next minimum is what? 5.
5.
Okay. And I want to maximize my weight of the graph, right? So if I can somehow bias my assignment of the graph edges such that Kruskal is forced to pick these higher value edges, it is forced to pick these higher value edges, then my motive is satisfied, right? Because then the edge weight, MST weight would increase, because Kruskal would be forced to pick up these higher end edges. It cannot pick up 5. Let's say it cannot pick up the 5 weight node.
Why,
Right?
sir?
Because why? That is the point. Why? The thing is, yeah. So if I want to restrict Kruskal from picking up smaller weighted edges so that my MST's weight is more, I would make 5 as a cycle node, cycle edge. So that
Cycle edge, yeah,
Kruskal does not, cannot pick that. Correct? So in 4 also I tried to do that. In 4 also is a lower end edge, it's a lesser value edge. I tried to put 4 in a cycle, but I cannot do that because since 4 is only the second minimum edge, wherever you put 4, it would Kruskal would pick 4 without forming a cycle.
That's
So
a very good question, actually.
right? But the
Yeah.
idea is clear, right? With 2 edges, you
Yes,
cannot
sir.
create
Now it's
cycle.
clear.
2 edges.
Yes.
So that's why I can put 4 anywhere, but I picked 4 over here so that I can create a cycle with 5. Now 5 I can restrict. So
5
Kruskal is
restricted.
forced to not pick 5. It cannot pick 5, right?
Yes.
And therefore now there is no other chance. Now wherever you put what, it would pick. So 5.
6.
So let's
5
say
is
6. It
you
will go
can
for 6.
pick
6.
6 over 7 over here, or 7 or 6 over here. Doesn't make a difference. And 8 over here. Right? I mean, if you take in any other chance, even if you put 8 over here, 7, 6, 8.
8.
So whichever you put, it would take the minimum one. Right? Wherever you put whatever, it would take consider the minimum one, because neither of this would form cycle. When I've taken these two, right? When I've taken this one and this one, then so it can actually pick either this edge also, it is not forming cycle, or this one would also not form cycle, right? Or this one would also not form cycle.
So we have to take minimum.
So yeah, so that means what? You can have 6, 7, 8 over here, or 6, 7, 8 over here, or 6, 7, 8 over here. It doesn't matter. But 5 if you put here, then I can restrict that Kruskal cannot pick 5, and that's why it would be forced to pick higher end edges. And higher end edges would make sure that my weight of the MST is more. So what is the weight of the minimum spanning tree now? 3 plus 4 plus
6.
6.
6.
So 13 is your answer.
13. Okay.
Right? You cannot force Kruskal to pick 8. I mean, it would have been best if I could have somehow forced it to pick 8, but I cannot do that because you saw it over here, right? So because whichever edge I put, I can put 6, 7, 8 in any of these 3 edges. But whichever edge I put 6, 7, 8, it would take the one which is the minimum. If I put 8 over here, it would take 6 from the other one. Because I cannot force any of these 3 edge to form cycle.
Definitely.
Right?
Yeah.
So it's very beautiful. You have to just...
Nice question.
So the answer for this is 13.
13. Yes, sir.
Okay, so that was for Kruskal and all week 5 content. Now let's move to week 6 quickly. Again, so what are your general doubts in week 6? Union find, again, from problem solving perspective, union find, we don't have any problem. It is mainly a approach to improve the Kruskal's algorithm's performance. So problem solving perspective, union find is not that important. The main important part is the heap algorithms from week 6, right? Heap algorithms and binary tree. So binary trees first thing is, so if I have a binary tree in order, pre-order, post-order traversal, right? All those parts should be clear with all of you. And let's say I give you a normal binary tree, right? A normal binary tree, not give you, can be reconstructed using, can I do it using only pre-order traversal?
No, you read in order and pre-order or post-order.
Exactly. So in order plus anyone, either pre-order or post-order. Fine. Quickly, let's do an example. Fine. Suppose a graph tree is like that. What would be the in order?
9,
9,
7,
7,
32,
32, then
11, 99,
11, 11, then
9,
99 or 8? Which one?
99.
Sure?
Yes, sir. Because 16 will be on the left side of 8. So 99 will also be on the left of it. Then 16, then 8,
Correct.
then 4, then 32, then
What, 44 or 64? Which one?
64,
64,
then
44.
44, then 19, and
Okay.
then finally 182.
Nice. So how did we do it very fast? You can just look at it from the top. Okay, look at it from the top and think that which one is coming to the leftmost part. So 9 is the leftmost. After that, if you see, so actually this graph, if I draw it properly, it would look like something like this. 4, then you come to 7, then you come to 9, right? And then here you come to 8, then here. Okay, I should have drawn it better. Anyways, so the thing is, this 7 should be actually a bit more far away. So 7, let's say 9, right? 7, then let's say 8, then let's say 11 and 32 and let's say 16, right? So you see that 19 is 9 is first, then if I draw, this is the second level, then if I draw, this is my third level, this is the fourth level, right? Then this is the fifth level, this is the sixth level, seventh level. This is how it proceeds. Okay, so therefore 9
So,
in the first. Yeah.
sir, in this in order, we take the left subtree first, and then
Then the value,
uh,
then
then
the
the
right.
root,
Yeah.
then the right.
Yeah.
Right?
So that's where that way you can do it and it would always be correct. But it would take you some time if you do not have practice, that you think, okay, I would go left, 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 then 9 is there, then value 7 would become, then I would go to right. In that way you can do. But if you can visualize this structure from the top, like in this manner, right, which is on the left and which is on the right, you can write it very quickly like we did. But if you do it, but the idea is that actual code is that every time you do in order, you actually do is you
Left,
put left, then node, then right.
not then right.
Yeah. So if you form it in the recursive function call, it would be something your in order, let's say the root node R. So you define in order, you call in order of R's left or R dot left, whatever. Left, then you do print R dot value, and then you again go in order R dot right. That's it. This is your in order function call. If I have to do it pre-order, all I have to do is take this at the top. If I have to do it post order, all I have to do is take this at the bottom. This is your code. This is your in order, pre-order, post order recursive code. Fine. Okay, so that's the idea, but now let's come to the problem again. So this is my in order traversal and pre-order now. Pre-order means what? At first the value, then the left, then the right. So
Right.
4,
4,
then
7,
7, 9.
9,
And then I would come back to 7, again go right, put 8,
then
then
11,
11, 32,
11, 32,
16,
16, 99,
and then come back to 4 and
30.
go right.
32.
Done?
Yes, sir.
Post order. Post order I would not do it for you guys. Practice it because I want to form the graph now, the reverse process. Now, how do we do the reverse process? The thing is, let's say if I'm doing it from pre-order, okay. By the way, is pre-order traversal written from the opposite side equal to post-order traversal? So if I write pre-order from this direction, will it be equal to the post-order traversal?
So do you mean that reverse of pre-order is post-order? Are you saying?
Yeah. So
No,
what I mean is is it post-order?
No,
19, 64, 44, and 82.
no, sir.
Yeah. Please, sometimes people make that mistake. Don't make that mistake in hurry. Reverse of pre-order is not at all post-order. Because this tree structure is not a linear tree structure. If it would have been a linear tree structure, then you would be able to tell that. So anyways, so now how will we do that to create the tree from in-order and pre-order traversal? Pre-order, yeah, go ahead.
We take the element from pre-order and then we check whether it.
Sorry, your voice got cut.
Yes, sir. First you check, take an element from the pre-order, then we find the particular position
Which
of
element? Which element? At first, which element?
4.
4. Now, in
4.
pre-order, we would take the first element, and in post-order, we would take the last element. So suppose whatever element was there in post-order, right? At the start, I don't know whatever it is, but at the end, I would have 4. Why? Because post-order, what does it do? It goes left, goes right, and then prints the node. So that means if when I'm starting from post-order from 4, I would go left and do my all the task, then come back to 4 over here, then go right, do all the task, and then come back to 4 again, and then print 4. So 4 would be, the value would be printed, root would be printed at last. So that means in post-order traversal, root, whatever element is at last, that's your root. And in pre-order traversal, whatever element is the first element, that's your root, right? When you have to construct the tree from pre-order, we start from left to right. What do I mean by that? It would be more clear now. And when I start, but just keep that thing in mind. And when we do it using post-order and in-order, right? When we use it post-order and in-order, then we start from this right to left. Consider the elements from right to left. Okay. Just the way we would do now from left to right in pre-order, in post-order, you would do it from right to left. Now see, what do I mean by left to right in pre-order? Take this node as first, right? In pre-order, you start from left to right. So take 4 as the first. So this is your root node. After that, what is there? 7. So this is the order that we are following, 7. Now you see in the in order, when you pick up 7 first, and you see in the in order, where is 7 lying? Is it on left-hand side of 4 or on the right-hand side of 4? So you see that 7 is on left-hand side of 4, right? 7 is here and 4 is here. So put 7 directly on the left-hand side. Then take 9. So you pick up each element from pre-order and see its corresponding position in the in-order and place it over there. So 9. So 9, where is 9 present? 9 is over here, which is even on the left-hand side of 7. So I have 7 at this position. So 9 is or farther left from 7. So put 9 here. After that, 8. So where is 8 present? 8 is present here. So it is just on the left-hand side of 4, right? But it is on right-hand side of 7. Right-hand side of 7, left-hand side of 4. So left of 4, right of 7.
Right of 7.
So here you would put 8.
So we are just using in and pre-order to
Exactly.
construct the tree.
Yeah. So now you go for 11. Next one. 11 is over here. That is on right of 7 and left of 8. So right of 7, left of 8. 32 is right of 4. So right of 4. Okay. I'm not repeating the whole thing. Just check it out. Should I repeat, or anyone has doubt? I can then repeat.
Sir, there are 232s. So how will it work?
232s? Okay. I didn't see that. So let's make it something else. Let's make it 99 is there. 99 is also there. Okay. 200.
So ideally, will it work for duplicates?
So it would work, but you would not be able to make out that which one is for which corresponding thing. But it would work. It would work because it is not even doing any value comparison, right? You are not doing lesser than, greater than, or anything. All you are doing is putting the node here and there. So it would work. Right?
It
So
won't create confusion, sir.
It would work. It would work. So let's proceed. Let's do 32 only. See what happens.
Okay, sir.
in a sense, it would be like the unstable sort, right? Because the positions of A and like inflection.
Actually the thing is, it would be stable depending upon your reconstruction. So if you can figure out which 32 is it, it's, see, it is stable. Why is it stable? I have two 32s and here I got 132. So which 32 is it? It is the left hand side 32 or the right hand side 32? While doing pre-order, which 32 is this 32 corresponding to?
This is the left one.
Is it the left one?
Yes, sir. The left of 11.
Left of 11, 32. Right? So this one. Now, when I'm reconstructing the graph, I mean the tree, then I have two conflicts. Here 132 is there, here 132 is there. Now, I don't know where I need to put it. Now, see, if I take this 32, it means it is on the left of 4 and on the right of 7. So left of 4, right of 7, and it is also left of 11, right?
Yes.
So I can put this 32 here. So I was able to take this decision that this 32, depending upon its relative position to 7 and 11, this 32 is between 7 and 11. Now this 32 was actually corresponding to this one only, right?
Yes, sir.
So let's say this is 32A, this is 32B. And suppose for the time being, you cannot see this A and B while you do the reconstruction. But even though you cannot see this A and B, but you can figure out which 32 is we are talking about at a particular point, because you are relative to this 7 and 11 over here, right? You can figure out this 7 and 11 is, this 32 is between 7 and 11. So you can put a 32 over here. What I'm trying to say is it is stable. It's not unstable, but it depends on how you are reconstructing the tree. I mean, if you reconstructed if you take this 32 like I did in the first case without seeing that, that already another 32 is there, then the reconstruction is unstable. It depends on how you are reconstructing. Okay, but it doesn't matter because it's the same node we are talking about. So stable or unstable, it's not a specific algorithm. It depends upon your implementation. You want to make it stable, you can do it, and otherwise also. But it doesn't matter because it anyway the same value node. So let's finish it up now. So 32. Let's keep it as 32 only. It doesn't make any difference. So then 16 is there. So where should I put 16 now? It should be on the right of 11. So 16. Okay, 99 is there. Where 99 is between 11 and 16. So 99 would come on the right because it is between 11 and 16. Likewise, you fill up the whole tree. So you take one from the pre-order and you check its relative position in the in-order and you put it in the tree. But so here I'm just differences. Here I'm doing from left to right. In post-order, I would do the same thing from right to left. So take the root node as first 4, put 4. Then let's say whatever element is here, take that and check its relative position and put accordingly. Likewise, we would do. So here I would do it in this way. And this element would be the last element to be considered in post
So
order.
in pre and post order, the only difference is the position of root node. Or
No. It is totally different. Post order is actually printing the left node first, then right node, and then the root node. So let's do the post order also. Because this question is anyway coming in any exam, in any place, these questions come. By the way, that means this question is not coming. I hope all of you know that. Anyway, so let's not take 32 and remove it. Let this 32 and let's say this is 200. Okay. So accordingly, 11, this is 200. And where is that one? This one, right? This is 200. 200. Fine. Okay. So now do the post order. What is post? How will we do? First move left, then go to right, and then you print. Post means, what is post? The printing is at the last. You are postponing the printing of the root node. Pre means you are preponing the printing of the root node. And in means you are doing the printing of the root node in the middle. Right? And that's why I wrote the code over there. Like, just check the a little bit ahead of the behind the part, bit ago of the session, you would see that I have discussed the code. So now you see how we would do post order. Go to left at first. So when I'm at 4, go to left 7. Go to left 9. Right? Move left. Move right. At the end, you do the print root. So 4, left 7, then left 9. And then left of 9 is nothing. Okay, so since left of 9 is nothing, what is the next step? So left of 9 is done. Then right of 9. Right of 9 is also nothing. So okay, then that is also done. So then print root. So now 9 is the root, so print 9. Okay, then come back to 7. Left of 7 is done because left of 7 we have traveled. So left of 7 is done. After that, right of 7. So go to right of 7. Okay, so now I am at a new root node 8. So again, start for this node, start the whole thing newly. So go left of 8. For each node, we would do start from this starting, right? Because that's a new function call. So from 8, I would go left at 11. From 11, I would go left at 200. And then I would say there is no left of 200, no right of 200. Now I would print 200. Come back to 11. So left of 11 is done. Okay. Now right of 11. Right of 11 is 16. Then left of 16. Right? Because 16 is a new call. So every time you go to a new node, you start from this line. Right? So I go to 16, then again start from left of 16. So left of 16 is 99. Okay. Now since 99 is again a new node, again start from this line. So left of 99. Nothing is there. Okay. So that means it's done. So 99's left is done. So then right of 99. Okay. Again nothing is there. So right of 99 is also done. Now print 99. Root. Print root. So root is 99. So print 99. Okay. Now therefore 99 is done now. So again revert back. So now come back to 16. So where were we in case of 16? Left of 16 we have done, right? We have explored. So left of 16 is done. Then right of 16. Right of 16, nothing is there. So it is also done. So then print 16. Okay, 16 done. Come back to 11 now. So now in 11, we see that left of 11 was already earlier done for 200 here. We did printed 200. Right of 11, 16 and 99 also done. So now left, right, both for 11 are done. This is also done. This is also done. So now print 11. Fine. And for 8 also, now we would see left of 8 is done over here. Right of 8, nothing is there. So then print 8. Come back again to 7. Left of 7, right of 7, both are done. So print 7. Come back to 4. Left of 4 is done, but right of 4 is yet not done. So go to right of 4, go to 32. Right? Now 32 is, again, when I told you, every time we go to a new node, we start from the beginning. Right? So, yeah. 32 is left. Nothing is there. Then 32 is right. 182 is there. Again, I came to a new node. Again, start from start. 182 left. 44 is there. Again, new node. Left of 44, 64. Again, new node. Left of 64, nothing is there. Okay. Right of 64, nothing is there. So print 64. Okay. Come back to 44. In 44, we have explored the right side, left side, right is left. So go for right of 44. Okay. 19. Now new node. So again, start from the beginning. 19's left, nothing is there. 19's right, nothing is there. Print 19. Fine. So do it in this manner. So 19, then I would go back to 44 and print 44. Then go back to 82. Left is done, right is nothing is there. So print 182. And then come back to 32. Left, right, both done. So 32. And at the end, you would print 4. So here you get the 4 as the last node. You see, this is totally different from your pre-order. It's not that pre-order and post-order are reverse of each other. The only point is in pre-order, the first node is the root node, and in post-order, last node is the root node. Okay, so pre-order, post-order, in order, creating tree using pre-order, creating tree using post-order. How will you do? Just start from this end and proceed in this way, one by one. Okay, and you need in order to find out the relative position and any one of the pre-order and post-order unit. Can I find if a binary search tree is given to you, if a BST is given to you, can I find the original tree, not the BST? If let's say if I give you a sequence of number and tell you that you have to form a BST from this sequence of number, and I also give you the pre-order of the or post-order, either pre-order or post-order. I do not give you the in-order. In binary tree, I gave you an in-order, and along with that, either pre-order and post-order or post-order to form the tree. But in binary search tree, if I give you only pre-order or only post-order, will you be able to create the tree?
Yes, sir. So in order is just a sorted version of the pre-order.
Exactly. So in binary search tree, we would be able to do that because the in-order sequence of a binary search tree is nothing but the sorted sequence of the number. So you know that anyway. You don't have to. So whatever pre-order has been given to you, just sort that list and you get the in-order. Or post-order has been given to you, sort that list and you get the in-order. So then you got pre-order and in-order or post-order and in-order. All you have to do is repeat the same step. That's it. Okay. So by the way, one not important, one trivia. If I have n nodes, right, then how many binary tree can I create using these n nodes? It's not in the exam, first of all. Just think of it. Okay. If I have n nodes, how many binary tree? How many binary tree possible? Then if I have n nodes, how many heaps? Heap means either min heap or max heap. Min or max, whichever. Both would be same. Whatever may be the number of min heap, that would be the number of max heap as well. So whichever you consider, how many heaps are possible?
So will heaps be one because heaps needs to be a almost complete binary tree.
Do I need to have sibling relation in heap? So
Oh, okay.
same element, both are min heaps. So I got 2 min heaps using 3 nodes. Same 3 nodes.
Yes.
So now you have to think, if I have n nodes, then how many min heap can I have? Okay.
2n heaps.
No, it's not that simple. Try to think about it. How many heaps are possible? How many binary trees are possible in n nodes? Okay. These two questions. And if you want, you can again, how many labeled binary tree? Labeled means what? So let's say you have n node, and with n nodes, suppose you have alpha number of binary trees. Alpha binary trees are there. Okay, for n node. Now if I ask you n unlabeled node, because so basically what I mean is, when I say unlabeled, what do I mean? So let's take an example and understand what we want to say. If I have 3 nodes, right? How many binary tree can I have? Let's do it for 3 nodes and see what do we mean by this question. When I have 3 nodes, is this a binary tree?
No.
The question is binary tree. It's not complete binary tree. It's not almost complete binary tree. It's only asking you how many binary tree. So is it a binary tree?
Yes, sir, it is.
It is a binary. Yeah, it is a binary tree. Why? Because the definition of binary tree states every node can have at most 2 children. Right? At most 2 children. So that means a node can have 0 children, which are the leaf nodes. A node can have 1 children, or a node can have 2 children, but not more than 2. That is the definition of a binary tree. So here I have 1 children for this node, 1 children for this node, and 0 children for this node. Fine. It's a binary tree. So this is a binary tree. Is this a binary tree? This is also a binary tree due to similar regions.
Yes.
This is also obviously a binary tree. So for 3 nodes, I can form 3 different structures of binary tree.
So you can also have like a angle bracket type of.
Exactly. Four, 5. And anything else?
No, sir.
Yeah. So the answer for how many binary trees can I have with 3 nodes is actually 5. Right? Now, if this is the case, now I tell you, just add one difference to this question is the difference is now these nodes are labeled. So I have, let's say, A, B, C. Will this make any change in the number of binary trees?
No.
So we will have to multiply with the permutation, like how many permutation of those 3 can be possible.
Exactly. So when I have A, B, C, then I can have the same structural form but change the labels and say this, because that would be a different binary tree. So this is ABC, I can have BCA. In the same structure, I can have ACB, and accordingly, whatever. And for each of this structure, I can assign the nodes differently and have a different binary tree. So then let's now generalize the whole thing. And that's what I was telling, as you correctly rightfully said, that we have to multiply it with the number of ways we can assign. That, like, if alpha is the number of binary tree alpha n is the number of binary trees, unlabeled binary trees, for n vertices or n nodes. And now if I want to ask you how many would be the number of labeled, right, for these n nodes, how many binary trees are possible where the binary trees are labeled, that would be into
N factorial.
n factorial.
Factorial.
Now what you have to find is what is this alpha. Okay, no need to find, I'm telling. I'm bad at this. So it is actually how we do that. We might not go into that detail, but the thing is, it is actually equal to okay. Now this number, at least in, I think I have told that, I mean, I have encountered or I have discussed about this number once or twice in some live sessions. I mean, this form 2n chosen by n plus 1.
So what is the denominator numerator?
2n chosen, 2n combination n.
Chosen. Okay.
Yeah. 2n chosen divided by n plus 1. Right? N is the node. You can do that. You don't remember, right? So let me tell this. How many possible ways you can do matrix associativity operation? So if I have A1, A2, A3, A4, how many possible ways I can bracketize these matrices? I can have A1 multiplied with A2 to so let's say let's put brackets like this. So A1 multiplied with A2 to A3 first, and then A4, and then A1. Right? I can do, let's say, one possible multiplication is this, or I can multiply A1 and A2 like this, and then A3 and A4 like this, or I can multiply A1, A2, A3, right? But A1, A2 first, followed by with A3 and then A4. Right? So these are different ways, and in fact, among all these different ways, the number of multiplication I am doing would be different. And that's what the matrix multiplication dynamic programming discussion was all about. That when I can bracketize these matrices in different ways, each of these bracketization would end up with different number of multiplication that I am doing in the process. Right? Result would be same, but the number of multiplication required to be done in each of these cases would be different. And matrix multiplication algorithm was finding out the minimum number of matrix multiplication. So basically it was finding out which particular bracketization scheme among all these possible bracketizations would land me up at the minimum number of multiplication. That's what matrix multiplication was all about. Okay. So Now, why I discuss that is this beautiful number that we discussed just here. If I give you a question as A1, A2, dot, 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 AN are the matrices, right? And I ask you how many possible ways you can bracketize these matrices, right? The number of ways you can bracketize these matrices, that is given by 2n chosen by n plus 1. Again, where n is actually equal to the number of matrices minus 1. So basically, for n plus 1 matrices, it is n. For n matrices, this n would be actually n minus 1. So basically, let's say if I give you A1, A2, dot, dot, dot up to A5, you have to take this n to be 4, right? But other than that, it remains same. So see, the number of ways you can bracketize matrices in 2n chosen by n plus 1. The number of ways you can, by the way, if you can bracketize matrices, you can also find out how many ways you can parenthesize code. So in coding, we check parenthesization, right? I mean, whether a code in C program or in other program, when parenthesization is important, we check whether the parentheses are closed or not. So if you want to find out the how many total possible outcomes are there, then also this number, your number of ways of parenthesizing is 2n chosen by n plus 1. Number of binary trees is given by 2n chosen by n plus 1. Okay. So there are other things also. There is, I mean, that's a separate problem statement. So there are multiple things which is given by this beautiful number 2n chosen by n plus 1, which are completely non-related. And this number is called as Catalan's number. It's like little brother of golden ratio. So if you, those of you who are aware of the golden ratio comes into nature at different points in random places, so but it occurs at different places, right? So Catalan numbers also, we can see it in different places. Anyways, just a little bit off topic discussion. Fine. So this was heap, sorry, no, binary tree and binary search tree discussion. Now let's do a little bit of heap problems, and then we can stop unless and until you guys have any doubt. So let's make a heap, min heap. Okay, so suppose this is a min heap that I have drawn. Now, if I have to insert an element into the min heap, so let's say I have to insert, give me a number.
62.
62. Okay, let's fill this up a little bit more. 112. Let's take it. So 24 is yeah. So now let's say I have to fine. This is fine. 62. Okay. So 62. So insert 62. Where would I insert 62? Always the last element, right? In heap, we would always
Yes.
insert as the last element. So left, this is 140 is left side, 62. This is my step 1. So step 1 is insert at last. Okay.
Yes.
Now, in heap, representation is actually done in the form of an array. We all know that. And how it would, the heap would look: 4, and then 30, then 20, then 120 serially.
120 serially,
35,
left to right.
and the last element would be actually
62.
150. Yeah. So initially 150, then I insert
Yeah.
62. Right. So this is the heap representation. So when you actually insert 62, suppose the array size is now one more, so you add 62 here. This is your step 1, and after that you make the changes. Okay.
Yes.
Now what are the changes? So here I put 62 now. So all I have to do is check your parent and parent and parent, like that. You check the chain of parents and you see that where your min heap property is getting satisfied. I mean, so basically you check whether your parent is larger or smaller. Since it's a min heap, your parent should be smaller. So if your parent is smaller in the first iteration only, then you don't have to do anything. If your parent is not smaller, your parent is larger than you. Now since it's a min heap, you should go at the top and your parent should come down. So then you swap it, and you do this swapping thing until and unless your parent is actually smaller than you. So in this graph, if we do, so you get 62, 140, 140 is greater, so 140 must come down and 62 must go up. So 62 and 140. And then you compare 62 and 120, again 62 is smaller, so 62 must go up and 120 must come down. Right, and then again you compare 62 with the parent, now new parent 30, and you see that okay, here 30 is smaller, so that's it. So this is how the heap looks after you insert 62. Now let's say the next thing is I want to do a, let's say, extract min. Okay, or delete min. Delete min. So what does that mean? How delete min happens is we would delete this 4, the minimum element 4. I would remove it. Okay. So let's remove 4. It has been given as an output. And in place of 4, what would we put?
140.
140.
Correct. So whatever is the last element in the heap, that we would put in place of the root. Exactly. So remove 140 from here. Put 140 here. By the way, what do we do actually in the coding? In this code, sorry, in this heap structure, initially 4 was here and dot 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 at the, let's say at this place 140 was there. Okay. What we do is when we remove 4, what we do is we put this 4 in place of 140 and
exchange.
Swap it and put 140 here.
And decrease the size.
Decrease the size, exactly. So 140 comes here, 4 comes here, and since this is an array, we would iterate through it using, loops and doing, and we would run the loop till the length of the array, right? So since now actually I put 4 at the end, and 4 is actually, we have taken it out, we have deleted the min, right? Deleted the minimum. So all I have to do in order to delete this 4 in that respect is I have to reduce the array size by 1 so that this 4 is not encountered ever again. So I do the swap, place 4 at the last index position of the array, of the heap, and simply reduce the size by 1. That basically simulates the deletion thing. Okay, fine. So now 140 has been placed over here. And after this, what would happen is why do we do this? The thing is, when I place the last element at the top, I can guarantee you that my left subtree and right subtrees are heap because I have not disturbed anything over there. So this part and this part are separately 2 proper heaps, right? I can guarantee that when I have placed 140 at the top, I can guarantee this thing.
Yes.
Right? Because I have not made any changes over there and they were initially heap. So these 2 subtrees are a heap in themselves. Only problem is I might have now lost the heap property at the root level because I have arbitrarily taken an element and placed it at the top. So that's why I have to restore the heap property by using heapify algorithm and apply it from top to bottom. So what do we do in heapify? You check 140 with your left and right child, and whichever is the minimum one, you do the swap with it. And you recursively do this swap until you reach the leaf level. So 140, 30 and 20, which one is smaller? 20 is smaller.
20.
So 20 goes to the top and 140 comes down. Okay. After that, what happens? Since now I have placed 140. So see, now I have not made any change on this left subtree part, right? I've only swapped 20 with 140 on the right part. So since I have not made any change on the left, and initially the left was anyway a heap, so I can totally ignore the left part now. It would still anyways be a heap. So now I have changed on right side, so I have to only apply heapify on right side. So recursively apply heapify on this 140 node, the place where I have done the swapping. So we check 140 with 124, whichever is smaller.
24.
24, so replace 24 goes here, 140 comes down. Again, same thing, since this part is not touched, so it remains a heap. I don't have to worry about it. So 30 should go up, 140 should further come down. And that's your heap. Right? So this is your delete min operation. And again, if you have to do again
Yes.
once more delete min, you put 150 on top, remove 20 and repeat it. So one question would come that given some element would be there, maybe there can be one or two insertion followed by some delete min, or a delete min followed by some insertion, some like that. Okay.
So we have to
So
heapify that.
heapify that, and that's it. So heapify we have discussed, creating a heap, all those things are discussed. Yeah, union find is new, no kind numerical doesn't come from there. Binary tree, binary search tree.
So does heap support duplicates?
Uh,
Binary search tree does not. So can heap support?
see, I mean, so these are very difficult question to answer. The reason for that is it all depends on implementation. All you have to do is put an equal to in the code, and that's it. So yeah, I am not able to tell you whether there is any specific rule which says that you can make it support, that's for sure, and you can follow all the heap properties while doing that. But I don't know whether, I mean, is there any place in the book somewhere you have seen this, that heap does not support duplicate?
No. Actually,
We have seen
BST does not support. That is why I just questioned.
BST does not
heap-
support
heap
duplicate.
supports duplicate. I think
Even
there can be more than
even
two
in
same
BST, even in BST, why does it not support duplicate?
Because there has to be a distinct left and right. If it's equal, we can't make sure whether to put it on left and right. Plus, it's a binary search tree. You just need to search a value.
Okay, fine. You have to search a value. So
If it's already exists, then there's no point of storing it again.
no. So what I'm asking is, so if I have a condition, so that is different. There is not, we don't have a point to store it. So that is different. So that is, I mean, it's not that it is obstructing something. It allows, I mean, even if you store the duplicate and you are going with the convention that every time I get a duplicate value, if I have to put it, I would put it on the left hand side. If a value gets repeated, I would put it on the left hand side. Or if a value gets repeated, I would put it on the right hand side. Suppose you get a, I mean, you can do it like that. I mean, so what I'm saying is, if I have, let's say 1, 4, 8, and let's say 2, 3, 8. 1, 4, 8, 2, 3. Again, I got an 8. So I come to 4. And then I come from 4 to 8 right hand side because 8 is greater than 4.
So what are you creating? This
A binary search tree.
okay.
So this is the sequence of numbers that has been given to me. So again, I got an 8 repetition over here. So I come to this 8 and I see that 8 is greater than 1. So go right. 8 is greater than 4. Go right. Now I got an 8. Okay, and in the insertion code I have written, if it is equal, then I would put it on the right hand side always. Suppose, or you can do it on left as well. I am taking on right. So put it on right. Fine. If this is my idea, will it obstruct me somewhere. Whether it's a point or not, that's something else, right? I'm storing it twice, but will it hamper anything with
So
respect?
we won't be able to add anything to the left of the bottommost 8. So like if we add 6, it will add to
Where?
the left of the first 8, and if we add 7, then it will add to the right of 6. It won't add to the left of 8.
Okay, so let's say from 4 I came I have to insert 6, right? So I came to right and then I inserted 6 here.
Yes, sir.
Then I want 7, so I can insert it here.
Yes, sir.
So
So you
then
won't be able to add to the left of the last 8.
does that break anything?
No.
Like
That's the question. That's what I'm asking. Is it breaking anything? Is it hampering anything of the binary search tree?
No.
what if we try to delete 8?
There can be two possible ways to delete it. When there are multiple nodes, when you are allowing multiple nodes, then you have to tell which node you want to delete. Let me tell you this. So when you see the dictionary data structure, right? Dictionary data structure implicitly inside it is a hash table. In Python, it's a hash table implementation. In Java, if you go, and if some other languages, maybe I might be wrong a little bit, I forgot the internal implementations, but in one of the languages, a hash table or at least a hash map is implemented inside the system, right, inside our language as a red-black binary tree. Now, what is a red-black binary tree? That's a different topic, but as of now, just assume it is a kind of a binary search tree. Okay. So even if you get duplicate elements in that, it always increases the hash map count by 1. Let's say the key value, so value gets increased by 1. And you can, it gets chained up, so you can again use that duplicate as well. Or in a hash map, let's say you are doing it on an object data structure, object data type. So let's say you have some 2 parameters are there in the object, 2 variables, A and B, but your indexing is happening in the hash map or in the, your indexing of the, or let's say in this tree, right? Let's say the hash map is implemented inside as a binary search tree, or let's say a red-black tree, but whatever, in a tree's way. And the indexing, that is basically these numbers, right? These numbers are corresponding to the A parameter, right? So then I can have the A parameter as same 8, but corresponding to that, the B parameter can be B1 and B2, right? Do different values. But my indexing is done using 8 only. So my every algorithm would work using 8 only. Right? If I have to implement, this is quite normal requirement, right? If you have this kind of object in real life, you would work with object kind of structure. And your searching would work on only one attribute, and other attributes would not be considered. Right? So in that case, you need to store duplicate. And trees are used for a lot of operations. So you have to consider duplicates. Okay. The thing is, I am not telling if some book states that in binary search tree duplicates are not allowed. I would not contradict that, but I would not support that as well, because everything depends on implementation. And yeah, so okay, let me ask, anyone has any other doubt corresponding to anything, any problem solving related type of doubt? Because week 5, I think we discussed each and every algorithm, solved a problem. And this week, heap is the important part. And yeah, so that also we discussed. Please, any topic that you have in mind, tell me at first. And then I would come back to one important point with respect to this discussion. No one, anything, no doubt? Okay, great. Anyone has any doubt still? Okay, so now let me ask this question. So by the way, I have to see who was actually in discussion with me regarding this. AVL tree would be discussed in the next week, okay? Sorry, not next week, in the next session, because that's in week 7. Yeah, so yeah, can you acknowledge who I was discussing this with? I cannot see your name.
Archit.
Archit, yeah, okay, fine. So Archit, have you done the DBMS course?
Yes, I'm doing it right now.
You're doing it correctly now. So
I have done it.
Okay,
Yes,
till
we've studied
Okay.
B tree and B plus tree.
you have studied B plus tree and B
Mhm.
tree. Okay. So in B tree or B tree is not used internally. B plus tree is actually used. B tree is just a previous version of that. Now, what happens? Why do we use B plus tree in DBMS? Have
Uh,
you gone to that part yet?
we use it to make the index for attributes.
Okay. So that means you do indexing using B plus tree. Just the same thing that you are doing here with binary trees and all that. B plus tree has added benefits that, I mean, so sure you have learned it over there. So basically it's an M-way tree. It has more branchings, and that's why its length is, I mean, sorry, the height is less. And that's why your log n value, log n base B value would be less. And that's also okay. So leave that part. But anyways, so basically it has a multi-way branch tree, and that's why your height is less, and that's why your search time is less. Mainly that is the broad point. That's why we use B plus tree for doing indexing, basically searching, because indexing is done just to search the elements, search the records faster. That's the whole motive. So in order to do a faster search, we do indexing and we use B plus tree. Now, what is this thing that what are the elements or nodes that you are indexing or in the B plus tree? Those are the records in the DBMS, right? In the data, your tables, whatever the records are there, those you are indexing. So when you are doing indexing, so let's say you do a primary indexing, that would be done on your primary key. But let's say you do some additional secondary indexing, or let's say you do some cluster indexing, not secondary indexing, let's say you do for cluster indexing. Okay, if you have not yet studied cluster index, so forget about that. What I mean is, let's say you pick up an attribute and you tell that, okay, whatever query I would run from now on would mostly be based upon this particular attribute. So let's say you have an attribute total marks in your records. For each student record, you have one attribute for every row. Every row represent every student, and one column is there which is total marks column. And you, whatever query you would be firing from now on would mostly be based upon the total marks attribute. Fine. Now, therefore, you want that, so that since most of my queries from now on would be based upon this total marks attribute, I want my system to work efficiently, and it should be able to find out the records very fast depending upon this total marks attribute. When you are in such a situation, all you do is you create an index on total marks attribute. That means you create a tree by using this total marks attribute as the node values, so that you do a login search on this total, so that the search for that total marks attribute values becomes login. Why I am saying this is, so when you put this node, I mean, when you create the tree with this values, what you are essentially doing is you are only using that total marks attribute to key the tree as keys or values of the tree, but you are doing it for the whole index. Sorry, not whole index, whole record. Now there can be a situation, not can, there will be a situation where total marks would be same for multiple students, right? But obviously the primary key for those students would be different. Correct. And other fields as well might be different. Primary key must be different, but other fields also might be different for those kind of students.
Yes.
But now in such a situation, what will you do? You know you use the B plus tree in DBMS. B plus tree, just as of now, think B plus tree is a binary tree. You know it is a binary, not binary, it is an M-way tree, but basically it's a tree. It works in the similar manner. It follows all the principle of this binary search tree, that you, if it is smaller, you put left, if it is larger, go right. So if you cannot store duplicate, what would you do in that scenario?
So one way is to forcibly make it you not a duplicate. We add the record pointer with the.
How would you do that? You are modifying the record, because you got 100 marks. I got, let's say, another guy, let's say Tilwani also got 100 marks. And since I got you as a duplicate, I reduced your marks to 99. How would you feel? So
what I mean is like something like 100 plus the something like the
Bonus.
for example, my roll number is 1, so 100, and then so it will become something like 1001 maybe. Not sure.
No, so that I mean, I didn't get exactly what you are telling, but I am getting the idea that you are trying to modifying that value somehow by some mixing it up with some other attribute or something, so that the identity still prevails. But I kind of do I am able to put the node in some other place. But as soon as you do that, you are basically moving your node to totally a different domain, right? If there is thousand something or whatever change in the now total marks you are making, you are moving it to some different place in the tree, and when the requirement comes to search, your 100 would not come, right? I wouldn't be able to. And if I have to apply the reverse mapping of the function, whatever function you are making changes to, for all the nodes, because I wouldn't know on which node I have made the change, that would be an extra problem. That's not an efficient way to do that. Okay, you can do one thing, which is what we call joint indexing, but that is a totally different kind of scenario, and basically that's a different the problem for that is a totally different problem statement. But anyways, so here we cannot do anything. All we do is, it's simple. It doesn't matter, you store duplicate, you keep it on one side. All you have to do is you have to follow the uniformity, so that if you consider that if I get a duplicate value, right, I am at a root, I am trying to put a, so let's say in this example, when I had 8 in the screen, just see, I have put 8 over here. So when I get another 8, I would put it on the right. If I'm putting on the right, I should keep in mind when I need to search, I would check that if I would check if this 8 is not that 8, I would go to the right, I would not go to the left. Okay, in the binary, in the B tree, all you have to do, if the record pointer is not matching, then you go to the right, you don't move to the left. That's the only decision that you have to take. And you know that because you are the one who is writing the code for insert. So you are the one who is also writing the code for search. So if you are inserting on right, you should search it on right. If you are inserting on left, you should search it on left, and that's it. That's what it takes. Only that much difference. And it works perfectly fine. Fine. So I wouldn't support if someone says that BST does not support duplicates, as long as you cannot give me a proper perfect reason where the code breaks, where the principle of BST breaks because of it. Okay. And because I gave you a practical scenario where it is actually using duplicates to store. It might not be binary tree, but it is like exactly like a binary tree. It's just M-way tree. That's it. Okay. So that's my point. If you ask me, heap supports duplicate or not, I would say yes, it can, because it doesn't matter. I mean, as long as at least now I am not able to think of a scenario where it breaks any particular principle of heap. But if it breaks a principle of heap, then it does not support. But as long as it is not doing that, it totally depends on your implementation. So yeah, as of now, I don't know. I wouldn't say I would. My answer would be heap supports duplicate. Binary search tree also supports duplicate. Yeah.
Okay.
Fine. Yeah.
So it
But yeah,
finally depends upon how we implement it.
at least I would try to go with that definition. But
Got it.
so 0 is a natural number or whole number is a whole different quarrel that is going on. In computer science, people say 0 is a natural number. Mathematicians say it is a whole number. So there are many such contradictions. Not contradiction. Contradiction is something which is formal. These are kind of arguments or
Hot
opinions,
topics.
hot topics, opinions, opinions. So yeah, so my opinion is both of them support anything you can, if anything which is implementation oriented, that I would always say it supports. Okay, as long as it is not breaking the principle of the core data structure. Okay, fine. Again, anyone has any doubt other than the ones that we discussed? Let me just see the mock ones, whether any other good question is. This one, can you tell? Consider a binary tree with 20 nodes where the number of nodes with 2 child node is 7. The number of nodes with 1 child node will be what?
So 5.
Great. How?
6.
So actually, I'm not sure about the answer, but mine came out to be 5. Actually, I was just solving it.
Nice. I mean, if this much luck prefers you in the exam, then you would solve it in 10 minutes, all the question.
No, sir, it took me a lot of time. Actually, I was drawing the tree, and as you were explaining, I was doing this question only.
Okay, nice.
So, yeah.
So let's see that. How many nodes are there? Total nodes? I also don't know the
20.
answer, by the way. 20. And what was told other than that?
7 nodes have 2 children.
7 nodes, 2 children. Okay.
So
So 2 children node, 7. Nice. Now, so whenever these kind of questions come where 2 children node is given and 1 children, how many single child nodes are there, how many internal nodes are there, how many leaf nodes are there, any this kind of question, or leaf nodes are given, how many internal nodes you have to count, any variation of this kind of question, when one particular type of node is given and another particular type of node count is asked, you take this way that I'm trying to do now, convert everything in terms of degree and apply handshaking lemma. Fine. So what do I mean by that? So I have 20 nodes in the tree. It's a binary tree that has already been told. So if it is a binary tree, I can have either 0 children node, I mean nodes with 0 children, nodes with 1 children, node with 2 children, right? So degree of nodes with 0 children or 0 childs equal to what? What would be the degree of a node which does not have any child? That means leaf node. How many
0.
degree? What is the degree of a vertex? A degree of a vertex is the number of edges. Since these are undirected graph, I mean, it's a tree, it's an undirected graph. So how many? So basically that means there is no separate notion of in degree and out degree. There is only one degree which is equal to the number of edges coming inside that vertex. So if I have 0 children for a particular vertex, that means it is a leaf node, right? That means it is a leaf node. Now leaf node means what? It must be connected to at least one node, then only it is a leaf, otherwise it's a disconnected, it's not a part of the tree. So that means what? The degree of a leaf node is always 1, right? Because it is connected to at least one node, right? So this is a leaf. So this is a leaf, this is a leaf. This is also one edge is there for this node, one edge is there for this node, right? It must be connected to at least one vertex. So the degree of node with 0 children or leaf node is 1. Degree of nodes with 1 child is what then? So let's say
Two.
this node, yeah, 2. This node, right? It has 1 child, only 1 child is there, it has only left child. So this is one edge, and obviously it must be connected to a parent. So this is one edge. Degree of node with 2 children is 3, right? Accordingly, so
If
1,
it is not a root node.
if that's the point, except root. Except root, because root does not have any parent, right? Every other node which would have 2 children, right? Let's say this 1 children, 2 children. So it has 2 children corresponding to 2 edges, but this node must be also connected to a parent one. Unless and until this is a root, it must be connected to someone. So therefore 1, 2, 3. So 3 except root. If it is not a root, if it is a root,
Then
root
2.
degree is 2. So this is our whole structure.
So won't the root degree depend like
Degree depend on the skewness. That is also correct. That if I have only one left side element in the root, so then it is 1. So we would take care of that. So basically, I should not say root is 2. What we should say is, okay. So let's proceed with the sum. I would tell what we would do. But just keep in mind that the 2 degree of node with 2 children would be 3 except root. Other than root, it wouldn't be. It would always be 3. Okay. Now let's proceed. So what we would do is, we know the handshaking lemma, which says that let's say summation of degree of all the vertices, if I do, right? So that should be what? Twice the number of edges. So let's do the summation of degree of all the vertices of the graph. So let's take for degree of 0 node, 0 children node. So how many zero children nodes are there? So basically how many leaf nodes are there? I don't know. I only know these two. These are the 2 points that are given to me in the question. So I don't know what are the number of leaf nodes. I would take L, right? L is the number of leaf. L into, what I'm doing, summation of degree. Okay, summation of degree. This left side is sum of degree of all nodes, which is equal to what? Number of leaf node into degree of leaf node. Degree of leaf node is 1, so 1 plus degree of one child nodes, that is how many nodes with one child are there. Is that information given to me? No.
No.
So let us take another variable x. So x into
2.
Plus, now see, 2 children nodes, 7 are there. We know that. Correct? But the thing is, I don't know whether one of them is root or not. Okay. So this, except this root thing, how would we tackle it is, we would do 2 into the degree, whatever the degree, that is 3. Sorry, not 2.
3.
Sorry, whatever this is, right?
7.
7 into 3. This takes care of all the possibilities, except when it is root, it should be
Minus
1
1.
less. Exactly. So this is what, so that this takes care of the root problem.
Minus 1, yeah.
So 7 into 3 minus 1. So this is what leaf node, this is 1 degree node, this is 2 degree node, considering the leaf node also.
So I understand the -1.
Okay, so I don't know whether a particular, so root node, if it is a root node, it might not have 3 as a degree, right? It would have 2 as a degree, not right. So that's why if I am doing it for 7, so I can write it as 6 into 2, 6 into 3 plus 1 corresponding to the root into 2. This is the whole thing. So 18.
Root can also have only one child, right?
Exactly. If it has one child, then accordingly the intermediate nodes with 2 children would increase, because the tree structure is maintained in that way.
Okay.
Right. So that's why I'm writing it in this format. Ultimately, both of them are same, but this is the more technically proper way to write it, because even if it is not the case, then the other node in between would have 2 children, and that's why this 7 into 3 would happen. -1 at some place it would not happen. I mean, the corresponding child node wouldn't be there. So anyways, so 7 into 3 minus 1, this is done. So this is summation of all node, which is equal to what? So by the way, let me compress it. L plus 2x plus what? 20, right? Yeah. Now this is equal to what? This is equal to twice into the number of edges. Right? So what is the number of edges in the graph?
20.
Is it 20?
Oh, sorry. 20 are the
19,
nodes.
19 edges.
19. 19.
Yeah. 38. Right. So L plus 2x is equal to what? 18. Fine. Now, I have 2 variables and only 1 equation. Any suggestions?
The sum of L plus X plus
Exactly. L plus X
plus 7 should be equal to 20.
Exactly. The leaf node,
Didn't get this.
0 degree node, 1 degree node, 2 degree node. This is 7. Right? If I have 0 degree node means leaf node. 1 degree node is X, right? X were the number of 1 degree node, and 7 were the 2 degree nodes. A binary tree can have 0 degree node, 1 degree node, or 2 degree node. Other than that, no other node can be present. So I'm summing up all the possible node, and we know that the number of nodes in the tree is 20. That has been given. Total number of node is 20. So that's why L plus X plus 7 is 20. Got it? Simply, what is the number? So I know in the tree there are 20 nodes, right?
Yes.
Now
Sir.
since it is a binary tree, it can either be a 0 degree node, 1 degree node, or 2 degree node, any node in the binary tree.
Yeah.
Right? So therefore, I am summing it up. Leaf node, 1 degree node, 2 degree node, that is equal to the total number of nodes. Fine. So from here, what we get? L plus X is
13.
So this is your equation 2. Now 1 and 2 solve. So basically X is 13 minus L.
X is
Or
5.
L is 13 minus X. L is 13 minus X. And plus 2X equal to 18.
Just
That
for
is
elimination.
X is 5
Okay.
and L is 8.
X is 5.
And L is 8.
L is 8.
So 8 are the leaf nodes.
So this is your number of 1 degree node, and this is your number of leaf node.
So this much we have to, if any such sum like this comes, we have to form the equation and
So
do, right?
this method is really
Won't
nice.
this-
Actually, what I did was I just simply created. I just created I just tried creating 2-3 trees like as per the condition.
Yeah.
And what I saw that the answer was coming out to be 5, so I
Oh,
wrote
nice.
5.
Okay.
Any shortcut methods?
This wouldn't take
I
time.
mean-
See, all this thing is taking time because we are discussing. Once you understand it, how much time does it take? 5-10 seconds. It wouldn't, if you can do it on your mind. But two things. First thing is 0 degree node, 1 degree node, 2 degree node. Degree of 0 degree node is always 1. Degree of 1 degree node is always 2. Degree of 2 degree node is 3 except root. So this format is always same. This equation is always same. That is equal to 2 into the number of edges. Now you see 20 are the nodes, so 19, since it's a tree, it's 19 edges would be there. 2 into 19 is 38. Once you get this, you get the equation and the total number of nodes, second equation. That's it. It looks like it takes time. It doesn't take time. It becomes
So this 2 times edges is because we are
which one? I didn't get. Which
this
one are you?
right hand side, sir. 2 times edges.
That is the rule. I mean, so basically, this is in your graph theory. Just have a revision of that. It tells you that when you take each vertex of a graph, undirected graph, and not undirected, in directed also it will work. Basically, as of now, think of undirected graph. If you have an undirected graph and you sum up the degree of each vertex, right, that would be equal to 2 into number of edges. So
Okay.
let's.
But in the question, there is no mention of. I think it's either undirected or directed.
Tree will be
So this minus one thing will be like common in all the like equations. Like we have to subtract this minus one for that leaf node.
Exactly.
Okay, sir.
So what is the degree of this vertex? 2. What is the degree of this vertex? 3. What is the degree of this vertex? 2. What is the degree of this vertex? 3. Sum it up. 10, right?
Yes.
2 into 5 equal to 10.
10,
That
yeah.
means
5
5 must
edges.
be the number of edge. 1, 2, 3, 4, 5. Now, why does it happen? This happens because of the handshaking lemma. Was this there in your graph theory? I hope it should be there. I
So
don't know.
we know that it is 2 into the number of edges, but we didn't.
So we have used this technique in solving questions of week 4.
But
We
you
represent
guys
DFS.
didn't know how it comes. It's not taught in the graph theory.
So because an edge is counted twice for each
That's
of
it.
the connecting node.
Yeah.
Yes, so
Because
that's why we same.
yeah. So if I'm considering degree, so let's say this node, what is the meaning of degree? So the number of edges which are connected, right? That is the definition of degree for this node. Now, when I'm considering, let's say this particular edge, right? When I'm considering this particular edge, so this edge is contributing 1 to the degree of this node and 1 to the degree of this node, right? So this node I'm calling its degree is 3. Why it is degree is 3? Because of this, let's say E1 edge, E2 edge, E3 edge, E4 edge. Okay, there are 4 edges, E1, E2, and E3, E4. 4 edges are there, and I'm saying this is 3. The degree of this vertex is 3 because of E1, E3, and E2. And the vertex, the degree of this node is 2 because of E4 and E1. Now you see, this E1 thing is contributing a value in this node's degree plus this node's degree. So when I do the sum of degree of all the nodes, the edge E1 is occurring twice. Likewise, if you see for all the edges, right, they are occurring twice. So for, let's say, for E4, what would happen? For this is 3 because of E4, because of E2, and let's say this is E5, suppose, and because of E5. So you see here that E4 is getting repeated here, E4 is getting repeated here twice.
2 times.
2 times. E2 is here, E2 is here, again 2 times. E5 is here, and if you draw this one, here its degree is 2 because of E3 and E5. So again you get E5 is here, E5 is here as well, and
So,
E3 is here, E3 is here.
So each edge is repeating
Contribute
twice.
repeating
for the
twice
two
for the
vertices.
yeah. So so when I sum up the degree of all of this, right? So this is degrees 2, his degree is 3, his degree is 2, and his degree is 3. So
10.
within, so when I sum up this whole degree as 10, this 10 is constituted by this 10 is happening because each node is contributing twice to the degree of a vertex, right? To the here and here. So you saw that. So therefore this summation 10 is therefore equal to twice into the number of edges. Fine. So
Yes.
we just use this factor of summation of degree in the previous example, where you sum up the degree on left hand side of all the 3 possible types of nodes of 0 degree, 1 degree, and 1 children, 2 children, and 0 children, and then you equate it with the number of edges, and that's it. Why that method? I discussed that method is, it's a general method and it does not depend on what is the problem statement. If the problem is asking you leaf node, if the problem is asking you 1 degree node, 3 degree node, let's say in more degree graphs, let's say k degree node, whatever it is asking, that simple approach would solve any kind of problem. Okay, and whatever data is given, let's say it gives you the number of leaf node is been given, but the total number of nodes are not given. No problem. All you have to do is put it in the equation and solve it. The unknown would be different, but your equation would be same. The variable would be different. You solve it for that variable. So that approach works for all kind of problem. Okay.
So for a directed one,
Okay, so
sum of in degrees is the number of edges, right?
Yeah. Okay. If there is any other doubt, you might ask, or otherwise we would end the session.
yes, sir, I think we can. Too much for today.
Fine. Okay.
Thank you, sir.
Fine. All the very best for your quiz.
Thank you, sir.
Right.
Thank you, sir.
Yeah. Welcome.